Okay, very good morning, all of you. Can you hear me all right and see the screen? Okay, very good. Okay, so I hope you're all doing well. Recall today we are at week 5 out of 6 weeks uh, for this module. Today we'll be discussing yet another neural network model, which is relevant for a specific structured data, which is very popular, uh, and that is known as relational data structures, especially when you think about knowledge graphs or any database that has a relation between two entities, A and B. So this is a special type of a structure compared to the structures that we have seen in images, where the relationship between the pixels were leveraged to develop neural network models. And if you look at the relationship between pixels, the nearby pixels are kind of ordered, and these are kind of a special graph, which is a Cartesian graph. But often when we are dealing with, say, recommendation systems or any other databases, many examples will follow as we progress today. You will see that the relationship can be not dependent on the spatial structure. For example, when we are looking at, or there might not be any spatial structure per se. For example, when I'm thinking about recommendation systems, recommending users for a certain commodity, that is very important task for any e-commerce platform. Now, the distance between two users is not relevant, but two user preferences about their purchases, they can be related, and often these are expressed in terms of graphs. If you think about financial networks, whenever we are thinking about any transactions that happen over any payment gateways, either Visa, MasterCard, UPI these days, there is an underlying graph always. The transaction happens between A to B, and there is a value of the transaction associated with it. And we want to do analytics over these payments. It could be, for example, uh, detecting fraud transactions, money laundering, and many other things. Or, for example, to suggest a portfolio for your financial assets. So there is many applications where graph play a predominant role. And we'll see how these multi-layer perceptrons, the neural networks that we introduced 4 weeks back, can be specialized to these graph databases. So that is the new content that you will see today. But before we do that, we will recap what we did in the last lecture on autoencoders. We will look into the a bit more in detail the particular class of autoencoders which are central to the generative models, variational autoencoders. So I already introduced this in the last lecture, but we will go through that a bit more in detail. And then we will switch gears towards another generative model, which is known as GANs in short, generative adversarial networks. And then towards the second half of today's lecture, so after the break, we will be focusing on the graph neural network part. So that's basically the plan for today. NLP, there's another lecture pending from this module. So that is scheduled next week. Uh, and we will go about discussing NLP in that lecture, right? So NLP, as I already mentioned in the beginning of this module, will not be looking at NLP as such. NLP itself is a module which is worth 4 or 5 weeks. But what we'll be focusing is on how to use deep learning for NLP tasks. And just to set the idea across, we'll be looking at one particular architecture, which is the transformer architecture, which is one of the latest and the most popular ones. So this is the plan for today. So quickly recollect what we discussed in the last class. We introduced something known as principal component analysis, PCA. So the idea is that you give me a data. It is in the unsupervised setting. The data, there are n examples and p features. And the goal is, now can I get a good representation of this data where I reduce p features, for instance, to two features, right? So for visualization purposes, in general, I would like to reduce it to, say, d features where d is much smaller than p. D is set to 2, good for visualization. D, anything which is less than T, which is dimensionality reduction. And PCA is one such tool to achieve go from X to X reduce. So for each of these data points, for example, if you think about this fashion MNIST data, I have 70,000 images of all these apparels and whatnot, accessories. All these points, the P was a 784 dimensional feature vector, right? So 28 by 28, we stack them in a long vector, we get 784. And each of these points, if I plot them to a scatter plot, you will be looking at that picture in a 784 dimensional space, which is beyond comprehension. Now, I would like to encode that into a lower dimensional space, and preferably, say, a two-dimensional space for visualization. You would like to just get a first cut of the data set, which is also called as the exploratory data analysis, EDA, and you would like to see, okay, how many clusters are there, etc., right? So how is the data behaving? And that is visualization. And oftentimes, when you reduce from 784 to 2, like what we also saw for this MNIST handwritten digit example, you might not get the clouds that the 9 or 10 clouds that we would like to, islands that we would like to want, but you would get one big blob because that is too much of dimension reduction. So PCA is a tool to achieve this dimension reduction, and a neural network, a nonlinear way of doing this, is the autoencoder, where the idea is that we have X, and then both PCA and autoencoders, if we recollect, they try to send this through some black box, which is doing some processing. We know, of course, much more about that black box, where you try to approximate at the output the input. The way we do that using PCA is through a set of linear operations. And note that all these are unsupervised, right? So the loss is basically between X and X hat. In semi-supervised, the loss is always between the output, which is Y hat, and some label, right? So this is our prediction or the estimate or the guess of our label, guess of the label or the regression output, right? So it need not be classification always, and this is our ground truth, okay? So we have that supervision. Now, whatever features we are extracting in supervised learning is based on the task at hand. For example, imagine the pipeline. You have an MLP, or in case of images, you have a CNN plus MLP. And if you look at all the intermediate outputs, or maybe the output before the MLP in the CNN pipeline, if you look at that, if the task is, say, to put a bounding box on an image or segment an image, then the features that the CNN layers would extract would be different compared to a classification. So, in other words, the features that it is going to extract are fine-tuned for the application at hand. In contrast, in unsupervised learning, you don't have a task, right? So basically, the goal is to extract features. And now there is no task, but I would like to extract features that are hopefully universal, which can be used for instance, for classification or regression. But now, since there's no task, there's no label because we don't know if we want to do a classification, a segmentation, a regression. We don't know that. So in that case, there is no label, but I still have to extract these features. And so what we do is we try to fit at the output the best guess that we have about the input. Okay, that is the loss, right? So that is what we are doing both in PCA as well as in uh, autoencoders. The only difference is that in PCA, our model for X hat was something like X W W transpose, but in autoencoders, what we do is you feed in X, you get X hat, but the model for X hat was that you have a nonlinear function which takes the input X, and then there is another nonlinear function that gives you the guess about the output. Now, this particular output of f of theta or the encoder is called as the latent feature. So these are analogous to the features that we extracted in the CNN, right? So, and then this is our g of output of g of theta is simply the guess of our input. Okay, so we encode and decode, and all this would make sense if the output f is, say, in d-dimensional space. So that should be smaller. D is much more smaller than P, right? So you compress. And while compressing, we want to preserve as much as information as possible about the input. And how do we say that you preserve most information? That is whenever we can get back to X hat, which is an approximation of X from that compressed input, right? So this is also something similar what we did. So we compressed and then we had to go back. So during that transformation, there should not be too much of information loss. And of course, there'll be information loss depending on value of D that we choose. But for whatever value of D that we choose, you should design this theta or W's depending on PCA or AE respectively, such that X hat is a best approximation of X. Now, this simple architecture can be tweaked to do anomaly detection, denoising, etc., as we saw in the previous lecture. So this is the gist about autoencoders that we saw in the previous lecture. What is important again is to remember that there is a bottleneck layer, right? So there's a bottleneck layer, which means that I go from P, D, and back to P. So P is much more greater than D, and which means that D is much more less than P, right? So that basically gives us this under complete architectures. Now, for the choice of neural network, it doesn't matter what you choose as long as you achieve this bottleneck. You could, for instance, uh, choose an MLP, or you could choose an LSTM, or you could choose a CNN, right? So only thing is like you need to go from say 784 to 30 to 784. So now this is again like a quick recap of how to build this architecture. So you basically stack that up into, as you can see, it's basically many single layer perceptron layers that have been put together. And except with the specification that you have the number of layers or the number of neurons in these layers decrease and then they increase, right? So I have to have that bottleneck, and that is how we build this there. Okay. So in all these aspects, there is no generation as such, right? So suppose the only possibility is it is giving you a generator, a possible generator. So for example, uh, if you want to think of a model that is going to give you an output, right? So what is our output? So x hat is g theta of some h latent. Now, given this latent variable, you want to guess how is my image generated, right? So this is our generator. So now what you see is that given a deterministic h, I know how to go from h to x, which means that I know how to generate my data points. For example, if you think of x as a cat, image of a cat, now how is a cat generated? How is the image of a cat generated? There is no mathematical equation. For example, if you think about any physical phenomena, right? So how does waves propagate, right? So or how does heat dissipate from point A to point B? There are enough mathematical equations, differential equations that explain the precise output that we measure. Say, for example, wireless signals you transmit from point A, you can accurately tell at point B what is the signal characterization of that signal that is received. But for images like cat or a dog, why does it look like that? There's no differential equation that explains how a cat is a cat or a dog is a dog. So there's no underlying generative model. So this is often called as a forward model, right? So forward model is that there is some latent variable that is going to give you the output that we measure. Forward model for all these physical phenomena are there'll be some underlying differential equation like a Maxwell equation or Schrodinger's equation, blah, blah, blah. But for most of the natural images, there is no such equation that explains. But now what we have is a generator. Fine, we have a forward model that takes from the latent space to the output that is desired. But this is useful for the number of tasks that we discussed in the last lecture. But imagine the following. Now, I would like to generate more examples, not necessarily explain how to generate one picture of a cat, but suppose I would like to generate many more pictures of cats or many more pictures that are similar to this MNIST digits. So I have trained my model. Okay. So I have trained my model, which could be this G of theta. But now I have trained this generator. But what is actually desired is I should be able to generate images or data points from this generator as many as I want. Now imagine the possibility, the following possibility. Suppose I train the generator, but every time I drive this generator or give as an input to this generator some random number. Okay, so for example, noise. Every time I sample, say, a random vector, feed that as an input, and every time this is going to output some MNIST digit. And what is desired? It is desired that the MNIST digit that it outputs is very similar, not the same image, but similar to the underlying data distribution. So there are like ones, zeros, nines, ones, etc. These digits come in various different attributes. For example, a one could be centered in an image, it could be rotated, it could be flipped, right? So there could be some background, etc. So we would like to generate more realistic samples as if they were acquired through some acquisition process. So if we manage to do that, then we can generate many more training samples. Having seen a few training samples, now I would like to generate many more of these as possible. Okay, I hope that story is clear. Now, with autoencoders, what we are trying to do is we are trying to map every example to a deterministic point in the d-dimensional space. So basically, I take my example, which is from, say, the space of features, RP, and then this is a smaller space, RD. So every example, I'm trying to put it here, and then we have a generator which is going to put it back to this point, right? So this mapping is kind of deterministic at this point. Now, to achieve what I was telling here, what we need to follow is something known as a Bayesian or a variational approach, where the hypothesis is actually very simple. And the way we achieve that is what we will discuss now as a part of this variational autoencoder. But the hypothesis is very simple. Now, suppose I want to generate these data samples, and I would like to drive this generator through some random numbers. What that means essentially is the latent variable, which was a fixed point, a deterministic point, needs to have some underlying probability distribution. So it has to be a random number, and there should be some underlying density associated to that. What is the simplest density that we can think of? Let's assume that the space where h comes is not deterministic, it is random, and we associate a Gaussian distribution to that. And what are the key attributes of a Gaussian distribution? It is its mean and variance. Okay, that once you know mean and variance, you can basically specify exactly the density function. If I know mean and variance, I can start generating samples from that distribution. So based on this simple idea that, okay, I have a generative model with the goal that I need to generate more samples, the first change or the first hypothesis is that we need to have a model for the probability density function PDF of the latent space. And once we have that, I know that space, I can basically sample numbers from that, and I can start generating data as I want. Okay, so that brings us to what is known as the probabilistic encoder and decoder. So the idea is very simple. Well, there is something that we need to take care in the process, which I will explain. But the idea is the following. So I have my data point. Each data point is again passed through this encoder, but the output of the encoder, we model this as some Gaussian with some variance and mean and variance, mu and sigma square. Okay, so now the question is, what should be the choice of mu and sigma square? Okay, and will this be Gaussian to begin with? Once we anyway have that, all I need to do is I need to sample from this distribution that we have learned and then put it back to the feature space. So every time I sample, since the input is different, but it is coming from the class that we have learned, we're going to recover back x's that were very similar to the data. Okay, so That's the basic idea. We will go through this a bit more in detail. Uh, so let's yeah, okay. So again, to contrast, this is a illustration. We'll come back to the math and the loss function once we understand this. So far, this was the autoencoders where every attribute, right? Every for an image, we have a latent variable. The way you should interpret is that, okay, there is some representation for each image. This is our H vector, and that H vector has some entries, and these entries could potentially resemble for this for illustration purposes some numbers where keep in mind that the H vector will not be interpretable in general, but this one is for the sake of understanding that, okay, if we feed in this image and there are this latent attributes could resemble smile, skin tone, gender, beard, etc. And those are some numbers associated with that. Now, once it takes that as an input, the decoder, it's going to reproduce this. Now, in variational autoencoder, what we are instead doing is, instead of latent attributes, I have latent distributions. So this will be a multivariate distribution where this H will have an underlying distribution. So it'll be the codings, what we call, will be having an underlying distribution. Now, if you, again, for the sake of illustration, if you just look at a point-wise distribution separately for each of the coordinates in H, if we model that as a distribution. So now each point for each sample will be a distribution. And as we can see here, now you're learning a certain distribution with some mean and variance for smile. So it's not just a point, but you also get the uncertainty around it, right? So that is what we are learning here. And then for skin tone, gender, etc., you basically learn a PDF. Now, what we can basically do is I can sample this PDF. Every time I sample, the red and the yellow dots that you see here is going to give you a different point, right? So if I sample red, it is more close towards 0. So the smile is like 0.17 compared to 0.23 on the yellow sample point. So you're basically going to sample this PDF. And then every sample that you get variations around X, the input X, which means that now I can start generating many more sample images. So this can be used to generate more training data. Okay. So I hope the basic idea with variational autoencoder is clear. The basic change is that instead of having a latent attribute, you have a latent distribution. So you're basically looking at a probabilistic encoder. Now, let's go to the math of it. Now, the way we do that is very simple and similar to what was going on in autoencoders. Okay, so you have an input data and the output, right? So now the output of the hidden layer where you want to get codings, what you're basically doing is that instead of generating the latent attribute, now we would like to generate a random vector. Now, how do we generate this random vector? You basically take, say, at this point, say hidden layer 2, the output at hidden layer 2, and this hidden layer output at hidden layer 2 is transformed into two vectors. One is the mean and the other one is the variance vector. How could we do that? So H2 could be, for example, H2 can be sent through some nonlinear function, a multi-layer perceptron, let's call it as f, say f of mu sum phi. This is going to give me a mu vector, and then this is f of phi sigma of h2. This is going to give me a sigma vector. Okay, so I have my input x. First hidden layer, say affine transformation plus bias, is going to give me hidden layer output 1. Again, linear transformation with a set of weights and biases, it's going to give me a hidden layer 2 output. Now, think of two MLPs. Those two MLPs are transforming H2 to mu and H2 to sigma. I get my mean and variance vector. Now, we have a standard normal distribution. This is this E vector. Okay, this E vector is basically linearly transformed to the Z vector. If E is, say, zero mean and covariance 1 identity, if I multiply this with sigma and add mu, Z will be Gaussian distributed with mean, sigma, and covariance matrix as sigma. Okay, so mean mu and covariance sigma. So when you transform any Gaussian random variable linearly, the output is also Gaussian, and you can easily compute the mean and variance. So now, as you can see, E I can generate easily, right? So it's basically sampling the random standard normal distribution, Gaussian with mean 0 and variance 1. I transform E to generate Z. How do I generate Z? Z is a function of mu and sigma. How do we generate mu and sigma? That's a function of hidden layer output, H2. So previously, we were simply using the output at this point as coding, right? Or latent space. If I do a contrast between variational autoencoder, so hidden layer output 2, I was using that as a latent space. Now, I'm still using that as a latent space, but I am generating a distribution from that point. Okay, so how do I do that? By simply modifying the standard normal distribution with mu, mean, and variance, which are derived from the latent variable H2. So now once I have this, the decoder part is exactly the same, right? So decoder part is simply again an MLP, which is going to take from the coding space. So for example, if coding is 10, which means that the Z would be of dimension 10, you go from 10 to 784, right? So there's again this bottleneck, except that now we have a probabilistic interpretation. Okay, so now with respect to the loss, I will come to that, but I see a couple of questions. Maybe I think there was a hand raised which vanished. If you still have that question, you can ask me. But
Thanks, Professor.
yeah,
So I had a question about the non-linearity that is being applied to H2. So I was wondering, do we have to have the non-linearity, or is there another way to generate from the latent space a
so if you look
distribution?
at, yeah, if you look at this, the mean is simply obtained by the dense layer. Now, one possibility is, see, I mean, nonlinear, like MLP is the most generic one. What one could do is you could also think of a linear transformation. But the point is that you would have something like this to get mu vector. Okay. So now if you don't want to have this, say, ReLU or anything, you can basically remove that and have a linear output as well. But the general variational autoencoder architecture is the following, right? So you use a nonlinear transformation. A nonlinear is a single layer single layer perceptron. Okay, so you can have a multi-layer perceptron here as well, depending on how much expressivity you want. Okay, you can also drop this and have a linear layer. So those are in theory possible, but now to achieve a better expressivity of the coding space, you might want to have multi-layer perceptron. Although in this particular illustration, we use a single layer perceptron, but you can, in principle, use a multi-layer or even a linear layer. Okay.
Professor, why are we coding underscore mean and coding underscore log where both are same, right?
So yeah, so I mean, here, okay, you basically don't look at the variance, but you have a log of the variance because of the exponential nature of the Gaussian distribution. But with that detail apart, so the idea is that you do different transformations of H2 to get mean and variance. So since W mu and W sigma are different, you have the two times, if that was your question. So basically H2 should be used to generate mu and sigma, and way we use that is basically use two different W's and weights and biases. Okay. So regarding Jayanti's question, so this is again an illustration, right? So the idea is that this point is now becoming something like P of H given X. Okay. And you will not have independent distributions. It could be like these H's could be correlated as well, right? So just for illustration, each of them I'm showing that as independent random variables, but that need not be the case. So depending on what value of sigma the network figures out, it could be that the features could be correlated as well.
Uh,
And
uh,
yeah.
so follow-up question. I mean, some of these are categorical and some of these are numerical, right?
So H in general is a real number, right? So
Okay.
basically, if you can see now, this is being modeled as a Gaussian distribution with some mean and variance, right? So this H would always be, say, a real number between minus infinity and plus infinity.
Okay. Meaning the features are transformed and it will be eventually a probability. All of these will be probability distributions only.
Yeah. So these are the latent variables, right? So the latent in the latent space, we have something like this.
Okay.
Now, in autoencoders, as we know, or variational autoencoders, you have X, and the goal is to have X at the output, right? So, which means that the space of input is the same space as the space of output. So, if X is, say, for example, containing images which are not categorical, the output will also not be categorical. But
Yeah.
having said that, so okay, that is something that has to be clear, well understood. But having said that, now suppose I have an image like an MNIST data where you have, say, a set of pixels between 0 and 1, and remaining ones are zeros. And then the output is also the MNIST image. Now, the way we could set up this loss function, it's twofold. First way is I can basically minimize the error, the MSC between the input and the output. Okay, that is one way. The other way is if I know that I'm dealing with images that are black and white or grayscale, after doing all the normalization, now I can basically treat each of these pixels as a 0, 1 variables. Okay, and then try to minimize the cross entropy between the input and the output pixels and average it across all the pixels. Okay, so whenever you see, like, say, categorical loss, that is what it means in the I think we also saw something like that in the example, right? So binary cross entropy. If you look at this, it is not that you're trying to solve a classification problem,
Yeah.
but if you're trying to minimize the discrepancy between the input and the output by treating each pixels as a 0, 1 label. Okay, that is the subtle difference. But the message is, the basic idea is that whatever is the space of the input, the output will always be the same from the same space.
Okay.
Yeah. Yeah. Okay, so Brindaban.
Professor, can you move forward one slide?
Yes.
Yeah.
Here.
So I think you explained, but I couldn't get this coding part. So coding mean and coding log variance. The same thing is written here. Keras.layers.dense. So how it is getting different result, mu and variance?
Yeah, so whenever we call a coding layer dense,
Hmm.
by default, every keras layer dense will have a set of weights and biases.
Okay.
So now again, if I call one more layer, so this will have, say, weight and biases as W mu and B mu. This will have, say, sigma and B sigma. So, which basically means that, for example, right? So here also, right? So if you look at this, the output at this layer would be different from output at this layer, right? So that is what we are. Every time we call a keras dense layer, unless we put an effort to say that use the same weights for all the layers. Unless we specify that, it's going to use a different weights and biases. Now, if it is going to learn different W for mu and different W for sigma, mu will not be equal to sigma. Do you see that?
Okay.
Yeah. So now when you're training all this, the point is you're learning basically the W1, B1, W2, B2, and then W mu, B mu, W sigma, B sigma, and so on, right? So you're learning all these weights and biases using backpropagation. Nothing much changes. Okay. So it's the same procedure, but every box that you see here has an associated W and B.
Okay. Thank you.
Now, yeah, related to question from Rupesh, it's not multiple distribution, so it is the same distribution of Z. H2 is still deterministic, but H2 and mu and sigma are also deterministic because it's a deterministic transformation of H2 to mu and H2 to sigma. But since we transform mu and sigma through a standard normal distributed variable E, Z becomes random. Now, what that basically means is every random draw that I make from this distribution, I'm going to get a new sample. Now, if I drive my generator, which is this particular box, with that sample, I'm going to generate a new output. So as you saw in this picture, so what you're basically learning is this distribution. Now, where we sample in that distribution, every time I flip a coin, I'm going to get a different output, but I know the distribution, right? So every time I flip a coin, I get an output and I drive my network with that output. So similarly, every time I sample this distribution, I'm going to get some point. So for example, imagine that this is like this is like a distribution that is almost independent. Like I can separate it as each of them being Gaussian, like in this illustration. So every time I sample, the red and the blue dots indicate the different sample points, two samples. Okay. So that is variational autoencoder. I hope that answers your question, Rupesh. Now, uh, let's take a look at this illustration of what is going on. So this is our input space, and this is our output space. What we are basically learning is this coding space. So I linearly transform and learn the underlying distribution to be Gaussian, mu and sigma. I sample those points. Once I sample those, I basically learn this distribution and I sample the distribution, drive my decoder with that distribution. So the idea is that I get some points in that space. Now that is what you see in the simulation going on here. So this is an illustration of variational autoencoder using TensorFlow. Okay, so what you see is you're training this network, okay, as the different frames that you are seeing in the animation is the training epochs. So as you can see, initially you would start with a random noise. If you can see it, you'll see like this when you don't have signal on your cable TV, you get this noise, right? That is white noise. So that is the first picture that you get. So it is random noise. As the training progresses, it is generating images that look very similar to the ones from the MNIST dataset. Okay, so this is another illustration of what is going on, although you don't see much going on. So here, what you see is that as now you see that it starts with a random blob, right? So everything is centered, which is say Gaussian with zero mean and variance 1. And as the training progresses, it is going to learn the mean and variance appropriately. And what you're basically seeing here is say a two-dimensional scatter plot, like very similar to the TSNE of what is being learned. So as you can see, everything that was centered as a blob is now being separated as the iterations progress. So these are some sample images that were generated from the variational order trained on fashion MNIST and some facial image databases. Okay. So any questions related to variational autoencoders? So this was the first out of subsequent many generative AI models. Okay, so autoencoders played a very important role, and the transition from autoencoders to variational autoencoders was the basic need to generate more data samples. Okay, so for example, if again, it's a natural question to ask, right? So suppose you have seen a face. Uh, can you generate or describe how a face looks like, right? So that is, if we ask that question to any human, that is going to a human, they are going to give a reasonably good guess, and there may be you might lead to a different picture when you start sketching based on the description, but we get the features, right? The face should have like okay, two eyes and then a nose placed in particular positions and so on. So we know how to generate uh, images, etc., right? By describing them. Now, can we ask a computer, an AI engine, to do the same? So in that sense, you're showing many of these facial images or handwritten digits or these apparel accessory images, and then having shown that, learn from this. Whatever you're going to learn, we don't care. But now I need to now start generating images or data from that underlying distribution. Okay, so that was the basic question that people started asking. And variational autoencoders were one of the first models, successful models, which were fine-tuned, made better, as we will see in the next part, to generate data. And as you can see here, it is reasonable, but the resolution, or one can easily say that, okay, these are kind of generated images. If you artificially generated images, if you look at all the background and the haziness in the image. Okay. So now what we will do is, having introduced this, we will look at the other very popular, predominantly used generative model for part of generative AI, which follows a different school of thought compared to variational autoencoders. Variational autoencoders, the idea is that, okay, I have an encoder-decoder architecture, excuse me, and the encoder is transformed to a probabilistic latent space, and then from that I sample to generate images. Generative adversarial network, it has two keywords. Generative, more or less what we have already understood. And adversarial is the key attribute of this network. Now, before we proceed further, let's do the simple exercise. I want you to answer this question in the chat window. So there are some images that I've put here. I want you to let me know if these images are fake or real, and if yes, which of them do you think is fake? And key in your answers. I can zoom in if you want. First and second one seems to be the answer from so far. Okay, so actually the images that we show here are all computer generated images, right? So you can see the transition in the technology from the images that were generated from the variational autoencoder to what we see at this point, right? So this is without a careful look, it's almost impossible to say that all these three are fake. And in fact, if you can go to this web page as we speak, every time you hit and enter, refresh on this particular website, it is going to generate new portrait facial images, right? So every time you hit, it is kind of the random number that you were generating in the generator for the generator input. The output is an image, which is very remarkable, right? So nobody can basically guess what is going on here, but that is what the technology has developed from variational autoencoders to this particular neural network model, which is called as the generative adversarial network. It uses a different training philosophy, as we will discuss as we progress. So this has tremendous applications beyond generating images of people. You might have come across these news articles related to deep fake, which is used for the primary intention is to generate more training samples, right? So I've taken a few, but I require to train these very large networks that require many more training data. And how would a computer interpret and generate these images, right? That was a basic question that people were asking, but that also led to many things that were not designed by many people who actually do not exist. They were created, they had identity, and then things were leveraged. But also, I mean, you could use this for some of the nice things that we will see as we progress. For example, like, okay, if you look at very similar to this is again like very similar. If you, many of you, I'm sure, like know about uh, Airbnb. But now, if you look at this, this rental does not exist. It's very similar. It's not just the generation of images. Oh, there is no basis of one and two being fake. It is so I don't know why many of you said one and two is fake, etc. Maybe because of the way the glasses were, or maybe there is some asymmetry that people recognize. But the point is that all these are fake, right? Not just one and two. And the other main point was that if you compare the images or the quality of data that was generated from variational autoencoders to this particular neural network generative adversarial network, there's a huge jump in the quality of images, right? So and of course, like, okay, I mean, we can dig deeper into the discussion of why one should be fake, etc. But the point is what I just said. But this can be used to generate realistic looking images, not just of particular attribute like a face, but you can generate a whole set of images like this Airbnb. And now you can imagine that, okay, you book this nice looking Airbnb, and that does not really exist, which is not what you would like to have, right? So this is some dark side of the story. So you can generate reviews, you can generate images that are looking very nice, etc. And you can generate these profiles. None of these would exist. Imagine getting into that world, which is actually problematic. So I encourage you to look into all this, right? So you can see every time you hit a refresh, you get a new Airbnb. You can basically yeah, these are not there, so hence fake, right? You cannot basically differentiate why this is fake. And actually it is not basically a mix of images that are out there. So every time you do hit a refresh, we will see how to generate, and it will be a nice exercise for you to uh, take these generative adversarial network models to start generating images, right? Or images or text, etc., to mimic what was there in the training data. So you basically take a lot of these Airbnb advertisements about people profile, how they describe their accommodation, etc. That goes as an input to the network, and then you start generating these images. So some more applications of GANs are beyond generating these fake images, which is much more interesting. For example, you would like to have a tool where you just give some segmentation of the images, for example, like what we see in this left. So especially for kids, this is useful to enhance their creativity, or also to bring their affinity towards art. So I would just want to create a photo of a landscape, but then you guide this network further with basic features, right? I don't know how to draw very well, or I don't know how to create paintings very well, but I can do a rough sketch, and it is going to generate images, right? So it's going to generate images like these different landscapes, meadows, river, etc. Similarly, this is if you look at this NVIDIA GauGAN, which is basically going to create these paintings. But what is also very interesting is that if you look at this particular game, I'm sure many of you know what this game is. This is a Pac-Man, which, if you want to code this game, will require 100,000 lines of codes. But now imagine that you're showing many realizations of this game where human is playing against this computer, and you show this to a network, and the network is going to see a bunch of these video frames, and now it is going to generate the game for you without particularly coding it, right? So this is basically mimicking all the scenarios. And this is what people have done with AlphaGo, and uh, uh, training different new moves for chess games and so on. So these are some applications of GANs, but oftentimes we would also like to create artwork, which is again of significant interest, particularly with artists who have a particular style. In this particular case, a Dutch artist called Van Gogh has a particular style of creating paintings. Now, of course, Van Gogh is not there anymore, but now imagine that, okay, you train a network by showing a lot of these Van Gogh type paintings, and you ask it to generate new paintings as if that was generated by Van Gogh. So as I said, the images or videos are not the main focus of GAN, but you can see the computer software, right? So you're basically mimicking based on images. It could be based on text. You're generating more text data. In the Airbnb example, you saw that it's not just the image that is generated, but it is the entire set of text, advertisement, profiles, etc., the entire package. Now, it has been also, as I said, used for reasons that we don't desire. For example, the deep fake that became very popular a couple of years back, where you take images or videos of celebrities, and then they start generating videos as if they make some statements, which is of course not desirable and not ethical, but these are the side effects of such technology. So generative AI is a very popular branch within AI, basically used to generate data samples. So you can generate these tools like painting or simplifying painting or assisting paintings, generating paintings, mimicking software codes, software profiles, etc., and generating, for example, CVs, making presentations, etc. Right. So it's not limited to the set of applications that I showed, but it's not also exhaustive. So now let's get back to how GANs work and what is the underlying principle behind training. So as I said, GANs have two keywords. One is generator, which basically means that given data, I give you a set of training samples. Again, we are looking at an unsupervised method, and I would like to generate more such samples. Of course, it is not interesting, for example, to generate the same set of images. I train on, say, 100,000 facial images. I would like to generate images that were not there. And beyond simple transformations like flip, rotation, or cropping of the image, but I would like to generate images that were not in the training sample. So it's not basically picking one out of these 100,000 and producing at the output. That is not the goal, right? So you would like to learn the underlying distribution and start generating samples from those distributions. If I manage to learn the underlying density function, then precisely, then the training samples will not basically have all the points in that infinite dimensional space, right? So now I can only train with a limited finite number of training samples, but if I know that distribution, I can sample that at infinite precision and generate all possible data that could have. So it has two parts and two boxes. One is the generator, the other one is the discriminator. The generator, as the name says, the goal of this generator is to generate images. It is again an unsupervised training technique, but the supervision is coming through this discriminator. So generator is a neural network which takes random input, generates output. Okay. The output of the generator is, of course, a fake image. Now, the goal of the discriminator is to discriminate between the fake image that is generated by the generator and the one in the training set. Now, the way the training process is set up and the loss function is set up is such that the goal of the generator is to ensure that it deceives the discriminator, which means that the generator will try hard enough every iteration so that it can successfully deceive the discriminator. Now, the discriminator is acting like an adversary, and its goal is to make sure that every image that the generator generates, it is going to catch with very high precision to tell that it is fake. Now they are playing a game with each other, right? So it's a game theoretic formulation where eventually at equilibrium, this network achieves Nash equilibrium, the so-called Nash equilibrium. I don't want to get into the mathematical details of that, but the goal is that eventually the generator wins this game and the discriminator loses. So the discriminator is pushing hard the generator to make sure that it generates images that it cannot discriminate. So basically, if every time the generator is generating some output and the discriminator is with very high accuracy telling that it's a fake image, then the images that the generator is going to generate will never become realistic, right? So you need to carefully set up this loss function such that the discriminator is going to eventually lose. So it starts with a very high accuracy, but the generator is going to catch up to the discriminator to make sure that it faithfully deceives the discriminator, which means that if the generator starts generating images that are very realistic, as if it comes from the training sample, then there's no way that the discriminator can discriminate and tell between it's a fake or real. Now, if the discriminator cannot discriminate between a fake image and image that is coming from the training data set, then it's very likely that we cannot also discriminate. So the role that the human would play to identify if the image is fake or not is being played by the discriminator. The generator is a generator network. And again, the philosophy that I mentioned before, it is sampling data. It should randomly sample data, drive with that random number as an input. It is starting to generate images. Now, once the training is done, you keep the discriminator aside. You only work with the generator model. Okay. So that is the basic idea, and hence the name adversarial. So the discriminator and generator are both trained in an adversarial fashion. Okay. So that's a pictorial illustration of what is going on. Now, depending on what you choose for the training data, right? So if you simply start using MNIST type images, it is going to generate MNIST type images. If you start using show different frames of a certain game, then that will be your training data. If the training data is a text sequence, the generator will start generating text sequence. So the output space of the generator and the space of the training data, those are the same. Okay. Now, during the training process, as you can see, the training data is never shown to the generator. Generator, the only input that it receives is this random number. Now, the way this loss function is set up, there is some backpropagation happening through the discriminator to the generator, as we will see later on. At any point in time, the generator is not seeing training data. The only input to the training data is noise. The input to the discriminator is the training data as well as data from the data at the output of the generator, which means that every time the discriminator is going to see, in this particular illustration, an image. Now, if it sees this image, the goal of the discriminator is to do a binary classification, tell it as 0 or 1. Okay. Now, training data, if it sees, it's going to give a real image. Fake, it's going to give a 0. But at some point during the training process, it should be such that the discriminator is not able to discriminate between the fake and the real images. Okay. So now this is the pipeline illustration. Let's take a poll at this point to self-reflect about what GANs does. Okay, so let's end this poll in a few seconds. I'm going to end this poll now. So, as we were discussing, the generator never sees a real image or an input, but the discriminator is kind of aiding the generator, although it is not seeing input images which are real, it is helping although it is fighting against the generator, the fight is actually challenging and helping the generator to learn the distribution of the underlying input.
Professor, one question.
Yes.
If the generator doesn't see a real image at all,
Hmm.
we never know what with just a random number noise as an input.
Hmm.
We never know what kind of image this could generate, and at the same time, in the training set as well, it could be totally. I mean, we should be knowing what should be the real, what should be the training set images, right?
Yeah, yeah.
For example, if the training set images are always remain, let's say, human faces, but this random noise input, it always keeps generating non-human faces. Then in that case, how does this work?
Yeah. So, yeah, the key is now there should be some mechanism to tie these generators and discriminators. Right now, the way you see this in the pipeline is they're two independent entities, but there should be something that attaches these two to achieve our goal. For example, if I don't marry this generator to discriminator to fight and help each other, what it will basically do is every time, like as you were describing, the training data could be facial images, and generator, it is generating some garbage which is not related to the training data. So what happens every time the discriminator is going to win the game, right? It's clearly saying that no, should not be from the training data because the discriminator is a binary classifier, right? So it is going to basically tell whether it is from the training data or not. Now, unless I tie that, the generator will behave independent of the discriminator. Now, what we will see as we progress is what is that string that attaches the generator to the discriminator, which will ensure that the generator is not generating something that will not make sense, right? So that is what we will see as we progress. So the training process itself, again, this is a pictorial illustration of what is going on before we get to the math, is basically a two-step process. So the as you see here, these are epochs, and we show like, okay, it converges in three epochs for the sake of illustration. The first attempt, the generator is going to generate some image. The discriminator very clearly says, no, this is not something that looks like from the training data. So it is going to declare that it's a fake image. The training progresses. The training progresses many attempts later. The output of the generator starts going towards how the input image looks like, but still the discriminator is going to clearly distinguish and say that this is not the how the input images, the class of input images should look like. Hopefully, as many iterations, whenever the training converges, the output of the generator looks very similar to the class of inputs, which is the class of cats here in this particular case. It is going to generate a class of cat. And this is what the output of the generator looks like. And now when the discriminator looks at this image, it is no more able to distinguish. And then that is when the training concludes. Discriminator is simply a binary classification. It is going to see the input. It is going to tell a 0 or a 1. Okay. So it is basically telling whether it is a real or a fake image. Now, for this training to proceed well as expected, what you require is the following, right? So you have two particular losses. One is the generator loss and the discriminator loss. Now, the generator basically has a very low accuracy to begin with. And then as the training progresses, this is the gen loss. And then this is what is actually desired. Now, the discriminator in the beginning of this is the epoch, training epoch, and this is the accuracy. A successfully trained GAN would have such a learning curve where the discriminator would have a very high accuracy to begin with, and as the training progresses, the loss of the discriminator should go down, and it should be worse than the accuracy of the discriminator should be worse than the accuracy of the generator. So this is the discriminator loss. Okay, so if you look at this, the discriminator starts with a very high accuracy. As the training progresses, its accuracy decreases and the accuracy of the generator picks up. And this is when the network has trained successfully, because the discriminator loss is low, which means that it is not able to, when I say loss, you should interpret this as accuracy. So when you see this, what that basically means is that the discriminator is no more able to distinguish between a fake and uh, a real looking fake output and a fake output, because the generator accuracy is very high. Now, suppose this is not what you decide. So this is something that is desired. And what I write below is not desired. Suppose you do training and then the generator, this is your uh, discriminator loss, and then you have a generator loss which is kind of increasing, and then at some point it is not able to perform well, right? So this is when the GAN is not trained properly or it is not behaving successfully. Okay, so this is not something that is desired. So this is my So, I mean, you could potentially stop your training at this point, but if this is a behavior, then it is not converging as desired, right? So, what we actually need is something like this. Okay, so now the discriminator is giving a feedback, but through the loss, right? So, you will see as we progress. Now, let's get to the training of the GANs. The training of GAN happens in two steps, and you will actually see what is being propagated to the generator. Okay, so the first step, you only train. When I say first step, it is training in alternating fashion, right? So you go do 1, 2, 1, 2, and so on. You are training this in alternating fashion. It's not that you complete training of 1 and then go to training of 2. So it is basically training in an alternating fashion. In the first step, you train the discriminator by holding the weights of the generator fixed. So when I say generator and discriminator, again, keep in mind that these boxes are nothing but MLPs or CNNs, which means that each of them have some weights and biases associated with it. And this is weight of a discriminator and a bias of a discriminator associated with it, right? So when we are having these boxes, they have some weights and biases, and all we are trying to figure out is what should be the appropriate weights and biases. In case of a generator, what you basically have is an image. If you're dealing with an image task, it should be an image generator, right? So similar to what we had in this auto encoder, the decoder layer. Okay, so the first step, the discriminator, you're going to learn the discriminator weights, and it need not be one step, but it could be a few iterations of step 1, few iterations of step 2, right? So it may not be like 1 and 1, but it could be like a batch processing. But so we have real images with us. Real, when we say real images, these are images from the training data. Okay, you take a sample, you have a batch of the sample. We know the labels of the training data, which are of course real. Now you also sample the output of the generator by fixing the weights of the generator in iteration 1. So you form this mini batch where you sample the training data and sample the output of the generator. You know the labels for that. you train your discriminator according to those labels. Doing backpropagation for the discriminator only, you learn the discriminator for the first few samples that we have generated. Next, what we do is we start training the generator. When we start training the generator, what this generator does is it backpropagates to the generator the discriminator loss. As we can see here, there are two yellows where the first step, the backpropagation, only the discriminator loss is backpropagated to the discriminator because we only want to learn the discriminator weights and biases. Here, in step 2, you freeze the weights and biases. So that means that in step 2, you're not changing W, D, and BD. Okay, so you're holding that as fixed, but then you evaluate the discriminator loss for those WDs and BDs that we learned in the phase 1. You backpropagate that loss, and that is actually going as a feedback. It is not, in other words, the loss is not simply 0, 1, but it is kind of a loss measured for that trained discriminator. You measure that loss, backpropagate that loss, and you train the generator weights so that that loss is optimized. Okay, so you see now that feedback mechanism is by backpropagating the discriminator loss through the generator loss. Okay, so again, let's take a look at how this works in practice. Phase 1, we have a bunch of training data samples. So for example, we are looking at MNIST data, 70,000 images, which are the training data. You sample 32 images. Now also sample out, sample say 16 images from MNIST and 16 outputs of the generator. So you form a mini batch of 32, mixing both real and fake images. I know labels of these 32 images in my mini batch. Okay. That gives me a way to compute the discriminator loss. We'll see what that loss function is as we progress. But for now, think that it is simply a cross entropy loss with which I can train this binary classifier, which is the discriminator. Now, I do that for a few iterations. I have some updates about WD and BD compared to the random initialization that I started with. Now, go to phase 2. You start generating images from the generator based on the WG and BG from the previous iteration. So if we are at iteration 0, WG and BG will be random initialization. You have the sample. So these are fake images. Now you pass that fake image through the discriminator by freezing the weights of the discriminator as we mentioned before. Now you measure the generator loss and backpropagate the generator loss to the discriminator loss. What does it say? If the generator loss is very high, as measured through the discriminator, what it says is now reduce the generator loss without changing much in the discriminator. So you're holding the discriminator as fixed. What you're basically looking at is how should I change my generator weights and biases such that if I use the same discriminator as what I used in phase 1, how will I be able to deceive that, right? So how will I be able to improve my generator loss? So as you can see, hopefully, that the generator loss and the discriminator loss are kind of coupled to each other. And in fact, what we'll see in the next slide when we describe this mathematically, that both of them are actually a function of each other. Okay, so this is how the feedback is working. Now, let's take this poll again to pause for a minute to understand what we just discussed, the two-phase training process of GAN and what is actually changing in each phase. And then I will be able to, then we should be able to appreciate the loss function better. Okay, I will end this poll in a few seconds. Yes, Rajai.
Yeah, Professor, I just want to know, like, this discriminator loss and generator loss, are they inversely proportional? Like, if the generator loss goes down, discriminator loss, I mean, if the discriminator loss goes down, generator loss, or they are direct, I mean,
They are related. We will see.
okay, sure.
Yeah. I mean, as I was showing in the learning curve, it could be that the generator loss is improving and the discriminator loss is saturating. So it need not be that if one increases, the other should decrease.
Okay.
Okay, I'm ending this poll. So as most of you have rightly chosen the correct answer. So it's a two-phase training process. The first phase, we only train the discriminator. And the phase, you should be careful, it is an alternating optimization, right? So you don't finish the training of the discriminator and then start training the generator. So you train for the discriminator for a few epochs, then train this generator for a few epochs, then go back, train the discriminator. So you do this in a cyclic fashion. Now let's take a look at this loss function, okay? So this is actually a very interesting loss function and the key to this adversarial training. So recall, discriminator is simply the binary classifier. So now if you look at all this, there are two functions that we need to optimize, G and D. G, when I say minimization with respect to G, the way you should understand is you're optimizing the weights and biases of the generator. That is this optimization. And optimization with respect to D would mean that you're optimizing the weights of the discriminator, weights and biases of the discriminator. Okay. So now let's take a look at this optimization problem. First step, what are we doing? We are optimizing D by fixing G. So G does not come into picture. Okay. G is fixed. It's not a variable. It's not a design variable. Okay. So now there are a few notations that we'll have to understand. So D of X is the output of the discriminator. What is the discriminator? It's a binary classifier. What is the output of a discriminator? It is giving us a probability, a soft value, whether the input was real or fake. So D of X is basically giving us a value between 0 and 1, which basically tells what is a probability that the input data was real. That is D of X. Okay. So now, given any data, which is a mix of training and the training data and the data that is at the output of the generator. So it's a mix of real and fake. What are we trying to do? We have labels with us. We simply train the binary classifier. So what is the real output? It is D of X, right? So you maximize that while minimizing the G of Z. What is G of Z? G of Z is the output of the generator, right? So cross entropy, you have positive and negative class labels, positive log, negative log of 1 minus that. Okay. G of Z. So if you look at this, it's actually very simple to see, right? So it's basically a simple binary cross entropy that we have seen many times so far in this program. G is the output of the generator. What does it take as input? Noise. So G of Z is basically the zero or the fake output. So what we want to minimize is log of 1 minus d G of Z, which means that you're taking either training data as input or you are giving the output of the generator as an input to the discriminator. Okay. So now when you do this, it is clearly going to train a binary classifier such that D does a very good job in classifying. Now, second phase, you're optimizing G. Okay. So now what does it do? When you optimize G, first term does not play a role. Second term, what are you doing? You're doing something opposite to what you would actually do to train a good classifier. What you're making sure is that G does a very good job such that the accuracy of your discriminator decreases. But this is for a fixed D. So what is that we should do to G so that for that particular discriminator that we had at phase 1, what should I change in G such that the accuracy of that frozen discriminator drops? So if you look at this, both of them are being trained to such that one of them is an adversary to the other, and eventually it can be shown that when you train, it would achieve this Nash equilibrium, and the accuracy of the learning curve would be such that the discriminator loss decreases and the generator loss or the accuracy, discriminator accuracy decreases and the generator accuracy increases. Okay, so that's about the loss function of the generative adversarial network. And if you see, this is again for the MNIST data set, what you would see is that as the iterations progress, initially the pictures are a bit arbitrary and random, but as the iterations progress, you would see that the digits converge close to 9, focus on one of the digits, maybe everything is difficult. This converges to 9 and the other one converges to 5. Again, the basic idea is that there are two networks. One MLP is the generator, the other MLP is the discriminator, with some reshaping that is required to get to that shape of the image. Generator is driven by noise. Discriminator goal is to basically detect whether the input is fake or not. But the way the loss function is set up is such that for a fixed discriminator, the generator is trained such that its accuracy increases significantly. And for a fixed generator, the discriminator is trained such that its accuracy increases significantly, right? So both of them are kind of fighting with each other to make sure that, eventually the generator wins, okay, this particular game. So this is about generative adversarial networks. I hope the loss function and the training mechanism of a generative adversarial network is clear. Now let's take a look at a code snippet. Nothing too complicated. So coding size, as always, is basically the size of the noise variable that you would give as an input. So you feed in a generator with a 30-dimensional random vector, and the output in this particular case, when you're training this fashion MNIST, would be 28 by 28. So as you can see, it is basically a collection of sequential collection of dense layers, right? So MLPs. Discriminator, as you can see, again is MLP, but the output is a 0, 1, which is a sigmoid classifier, right? So sigmoid output or logistic loss function. The loss function is basically the binary cross entropy, right? So as we saw in the previous slide, you can use GANs with CNNs as well, except that you start with, say, a certain coding size. Now if you are using a dense layer, and then you will have to use this transpose convolution layer to go back to this higher dimensions, 28 by 28 or 12 megapixel image that we require. So that is done with this transpose convolution layer that we introduced in the last lecture. So you can use it with MLP, you can use it with CNN, you can use it with even RNNs, basically to generate a sequence of the time series data. It's not that you have to use it for static data, but the whole generative process. For example, if you want to generate music, right? Or if you want to generate these games that I showed in the previous few slides. So you'll have to have some sequence modeling approach as well. Okay, so that basically brings us to the last slide of this generative AI aspects that we looked at. Without worrying about generative AI part, what is actually important is this dimensionality reduction and visualization, which is an important tool by itself. Without worrying about neural networks, deep learning, etc., visualization, doing exploration of data, which is EDA, is an important tool by itself. PCA and many other tools help us to achieve that, right? So that help us to achieve that objective, like TSNE, PCA, autoencoders. But these autoencoders can also be used for generating more samples. For example, we saw that it can be used for partial training with partial label data. Suppose I have 70,000 images, but only say 1% of them have labels. Now, instead of training a supervised model on that 1% of the data, how do I leverage the entire training data and do something on top of that, where I can also utilize those 1% of labels that I have, right? So this is called a supervised pre-training procedure, like what we saw before. But you can also generate images, sequence, text sequences, time series data using these autoencoder, which is Bayesian version of an autoencoder, probabilistic version of an autoencoder, which is the variational autoencoder. And a second alternative approach to generate data is the GANs, generative adversarial networks, which do not follow the principle of probabilistic way of modeling the autoencoders, but the probabilistic input driving a network with a random input. That idea remains the same, but the training procedure is slightly different from the variational autoencoder. So this is called GANs. Now, there are variations around GANs. For example, think about this. I train the GAN with a set of MNIST images, handwritten digits going from 0 to 9. But now, every time I drive this GAN with a random vector, random noise, it could generate any one out of these 9 digits. But suppose I would like to generate, after training this GAN, I would like to generate only a particular class of data points. For example, I would like to generate only ones. That is done by a variation of GANs called as conditional GANs. Okay. Along these similar lines, but with a different training philosophy, what has become popular in the last year and a half is again another important generative model, which is called as diffusion models. So if you're interested to understand more about these generative models, and see what are the latest developments in this area, one would look into what is known as diffusion models. Mostly these are used for vision-based applications like images, video generation, AR, VR applications, but have been also applied for other generation purposes as well. Okay. So with this particular note, now we will pause for a break. and then resume back maybe at 11:15 to look at, we'll switch gears and look at the graph neural network part. Okay. So let me see if there are any questions. So Sandeep, I guess your question was answered, right, in the while discussing the loss. And Rupesh, so training is done for every new data generation. So in GANs, you do this for all the training data. You do training of discriminator and generator for all the training data, right? Suppose like 70,000 images in your training data. You train your discriminator and generator on all the 70,000 images, right? So once the generator and discriminator are trained, you basically discard the discriminator. That's of no use. Now, generator is trained, you simply sample random noise, feed that as an input to the generator, right? So that is what the generation is about, okay? So new data generation, there is no training that needs to be done. You freeze the network. I hope that answers your question. I don't see any particular question. So at this point, let's pause for a break and then
Professor,
ah,
I have a question.
sure.
Are these GANs used for image and video classification alone, or are they used in some other areas in cybersecurity to protect the
Yeah, I mean these are used for generating keys. For example, in security applications, security keys
Yeah.
which are not predictable. For example, like if you think of any key generator in security, it will be through this
Yes.
AES protocols. But these are known set of limited keys that one could generate. Now you can train again to generate keys that are not known, right? So which basically come from those class of keys, codes, but you can generate new codes, which are useful because since these are kind of random but have a certain particular pattern in them, these are often difficult to break.
Okay.
And these are also used for radar waveforms. For example, radar waveforms, again, you would like to generate always a radar. Radar is basically for detecting planes and
Yeah.
in case of military applications, some stealth drones, etc. Now, often what is important is to generate these codes that people cannot easily decrypt or
Okay.
deconvolve in the context of signal processing. But oftentimes, the traditional codes that people generate are through certain protocols that can be easily deciphered, right? Or may not be that easy as I make it sound. But now imagine that I should be able to generate codes that cannot be easily perceived otherwise.
Yes.
So yeah, so as I was telling, like the applications of these generative models uh, are actually yeah, it's a very popular area in neural networks or deep learning with applications ranging from images and text to much more.
And is this also used in ChatGPT like applications, which is something that keeps learning from the user and to protect the
So
model from?
ChatGPT, most of the GPT models that we are aware are currently limited to text. Although
Yeah.
there are like few multimodal models that generate, but those are not used to generate fake images, right? So it
Yeah.
basically is to generate something much more useful, deriving from what is already out there. You would not ask ChatGPT to, I mean, for example, you can ask ChatGPT to generate like a plot of, say, sin X, but
Yeah.
that is not the goal behind these generative models. The generative model is like, okay, say, simulate a cyber attack or generate a cyber security key. right? So
Okay.
those are more applications, and ChatGPT would not be able to do that.
And the discriminator model, can it maybe discriminate between what to learn from? I mean, if there are some user prompts, which user prompts to learn from and which not? Is that the job of the discriminator, or is GAN used, or is it something else?
No, so discriminator, as the name in English suggests, its
Yeah.
goal is to distinguish between different inputs,
Okay. Yeah.
right? So it is simply a binary classifier at this point. Now, you can use this idea to basically design better prompts,
Yeah.
right? And automatically generate better prompts. Maybe people have done that. I'm not
Yeah.
aware, but yeah, discriminator is simply a binary classifier, and you can ask to is to generate good or bad prompts, for example, right?
Okay.
Yeah, but you can also maybe use GANs to for prompt generation or fine tuning, automatic fine tuning in the context of LLMs.
Okay. Thank you.
Okay. Okay, so let's pause now. We are already like overshooting with respect to time. So let's try to get back at 11:15 or 11:20 to continue. So related to Praveen's question, yeah, so that is actually another very interesting research area, predominantly uh, at this point pursued by Google and all these big data companies which house big data. So there is actually currently there is no way to distinguish between what is fake and what is generated. There's no open source way of generate looking at that. But most of these companies, what they do is something known as watermarking. And watermarking, way they do that, for example, like many of these generative models that they have, they also kind of watermark these data, which is of course like not apparently seen in the image. And that is what is used to distinguish between who has generated it and uh, whether it is fake or something that is genuine, right? So that is currently what is the practice that is being followed, especially with all the new rules that are put in place, right, with respect to ethics involved in AI and many incidents that are due to these deep fakes, right? So many incidents and lawsuits that were out there. So that is something that is currently being pursued. And what is the best way to watermark an image, robust way? So this is kind of like getting into the security aspect, but that is what is currently being pursued as well. So if you look for watermarking and watermarking Google and fake or generative images, you would see uh, more about that. Yeah, so that's the goal, right? So it should not be very obvious, and it is hidden in the metadata and not the image per se. Okay, so let's proceed further to the another topic that we planned to cover in this module. This is for relational data. So if you look at what are the important trends that people pursue in neural networks or AI, graph neural networks is one of the top technologies in that list. And many companies, because of the applications underlying it, also pursue graph neural networks. Um, in one way or the other, right? So mostly these are e-commerce based companies, and Netflix, like recommendation systems, etc. But graph itself is it's a very powerful mathematical object and a software construct to store data, especially when we have relational databases. So, like how MLPs, for instance, could be used to do image analytics without exploiting the structure. We saw that, okay, there is a good use case to develop a new AI tool that leverages the underlying structure in the image, right? So, for instance, like we saw this 12 megapixel, if I want to do image analytics with an MLP, the number of parameters should grow proportional to the size of the image. Now, given that, we had to develop this convolutional neural network architecture. Now, similar need arises to exploit the underlying structure. And it so happens that images have the structure that is nicely ordered because of the domain they underlie, the underlying domain. But in graphs, that underlying domain is very irregular, and there needs to be newer tools, especially neural network based tools that are leveraged to do analytics over graph data. So, like ML and the transition to deep learning, graph neural network is a newer tool to do graph analytics based on neural networks. So there have been many tools to do graph analytics which are not neural network based. For example, to do classification, we had tools like XGBoost or simple logistic regression and so on. And we saw that, okay, using neural networks, we can also achieve maybe solve similar problems, achieve better results. So the similar analogy also holds for handling graph data, right? So there are tools which are not neural network based. For example, recommendation systems, you might have heard about something called as collaborative filtering, and many other graph tools like spectral clustering, etc., which have been out there for a few decades. And neural networks is yet another way of using the MLP or the perceptron idea to solve those analytic tasks much more efficiently and with better accuracies. So uh, what we will focus on is basically the neural network way and give a sense of what is going on with graph neural networks and how could one potentially learn representations with graph data, what is graph data, and how to set up a graph neural network. So that is basically the limited purpose of whatever we will cover in the rest of today's lecture. So for starters, what is a graph? Graph is basically a collection of nodes like what we see here, and then each node will have an attribute. So there'll be a feature vector associated to each of these nodes. And then what we would like to do is we would like to process these graph structure data, including the features, and then solve problems, very simple problems like, for example, whether there is a link between these two nodes. For example, imagine that this is a social network and you would many times get a prediction on LinkedIn or Facebook or Twitter to follow a certain page. You want to be friend with this particular person, etc. Those recommendations can be treated as link prediction problems. We'll see many more manifestations of these such applications as we progress. But the goal is like as we did with CNNs, what we have is we have a graph, and then the goal is to extract features using a neural network model, which is a graph neural network model abbreviated as GNNs. And then you get features. And once you get features, again, as usual, you will have to use some kind of an MLP to perform any downstream task, right? So we will see many examples, many different examples of how to use graph neural networks and what are the typical use cases of graph neural networks as we progress. So the material that I'll be using, it's not part of the Geron's book, but I'll be sampling a few chapters from this very nicely written monograph called Graph Representation Learning. It's available online, and there are some tools. And if you're interested, there is also this nice set of video lectures out there on machine learning with graphs. Okay, and so there are tools from TensorFlow, there's Stellar Graph. If you're interested in PyTorch, then there is something called PyTorch Geometric or Deep Graph Library, DGL, maintained by Amazon. So there are many tools similar to what we did for MLP using Keras. I think Keras also has GNN based libraries, but maybe not as extensive as PyTorch geometric or DGL, right? So there are basic GNN architectures out there. So just to give a context of what is graph neural networks and some of the use cases and how powerful these are, if you are using Google Maps to go from A to B, what is underlying Google Maps to predict the best route, to predict the expected time of arrival is a graph neural network. Whenever you say give a search for a destination, what you would get is a couple of routes, and it's also going to give you an expected time of arrival, right? In some cases, depending on all the feedback mechanism, etc., the ETAs can be quite reliable, but also it's up to a noise based on the instantaneous measurements that Google also makes. But the idea is the following. So what you can imagine is that if you ask to go from point A to point B, you basically get a set of junctions which are nodes of a graph, and then there are streets, roads connecting these junctions, which are nothing but edges. Now, what you basically do is you measure a lot of information along these junctions, along the route, which is information sitting on the edges. These are attributes. And now you would like to use that information to predict something about the the next possible node that I need to visit. And you do that in sequence to achieve at a certain route, which is a trajectory, and then certain attribute about the end node, which is the expected time of arrival, right? So what is the expected time of arrival? And of course, you use predictions to do this, but also use some meta information to make it but a bit more reliable. It's not simply the naive GNN that we would use, but along with many other engineering that Google does to basically um, give you the best possible routes based on ETAs, right? So, and if you want to do kind of a prediction of best routes, for example, may not be in India, but many places where you would like to see what is the best resource that one has to dispatch. In case of dispatching ambulances, what is the best route to take, or what is the best resource allocation in case of retail or storehouse management. Graph neural networks play a very important role there as well. So some of these pictures you already saw in the beginning when I was introducing this module. For example, this particle rendering that I mentioned to simulate physics, what is basically used as a graph neural network to exploit the local topology. So what we see here is a graph neural network in action, where you see certain physical phenomena, either throwing these particles in this cube, how does it behave? It's basically simulating physics without knowing or modeling the underlying equations that govern these physical reactions, or like how does water flow through these ducts and cracks to monitor any fault diagnosis in oil refineries or etc., or oil rigs. You could use these neural network models. AlphaFold, I already mentioned about this protein unfolding. Again, graph neural networks play a very important role. But what you have not seen so far is, say, for example, if you're interested in bioinformatics or pharmacy related applications, very similar to what I mentioned before, predicting friends in a social network, you can also use that to predict interactions or repurpose drugs in pharmacology. For example, what you see is like a multi-layer network where you see in orange interactions between proteins, right? So there are many proteins and there are many genes. It's a genomic network, and whenever we design a particular drug, these are designed to target certain diseases, and the way they do that is by targeting certain proteins, right? So similar to what I was explaining, if you remember this AlphaFold. Now there is an interaction network between the drugs, and interaction network between the drugs and proteins. Proteins should be understood as diseases, and drugs are chemical compounds. Now, often what happens is that whenever we go to a doctor with some issue, or for some of the drugs that one has to take for their entire life, like hypertension, diabetes, you're always taking multiple drugs, or you are on a certain drug for a longer duration of time. Now there is a new diagnosis, and then you need a new drug. Then what is important is to see if there is an interaction between two drugs. So that is often based on the know-how of a doctor. But if you want a more reliable mechanism, especially when people don't use generic medicines, there are many companies that manufacture the same drug, but maybe with different variations or combinations. What is important is to see if you take two drugs, for example, the statin with, say, this antibiotic. If you take this, then what is the reaction that might have? The reaction has basically given some known interactions between these drugs. You're trying to predict a link, whether there will be an interaction, and this interaction could be something that is uh, a mild one, or something that can be life-threatening. For example, if you take the ciprofloxacin and the statin medicine, RT is a bradycardia side effect, or it could be some other side effect, which is a GI bleed, right? So one would like to have an automated tool to predict these interactions based on a simple query. And you might not have interactions measured or studied in detail for all possible drug pairs, right? So you have to put basically somebody on a human, some human on a trial to test for all possible combinations, and that is quite cumbersome, as one can imagine. Like nobody would like to risk that, right? To not put somebody on a risk to measure the side effects, or you would like to also use some other tool to measure these side effects. So a similar use case is when you would like to order dishes on, say, Swiggy, Zomato, or Uber Eats. Uber Eats actually uses graph neural networks to do prediction recommendation of dishes. It is very similar to prediction of movies or TV shows on Netflix, based on user interactions and interactions by similar nature of people. For example, you're watching a lot of these action movies, and then very likely you would like it will predict an action movie. That is a no-brainer. But now it could be that with a profile you're watching a mix of action, romance, or comedy, all these different things, then it becomes a non-trivial exercise and to predict. And all these platforms, they would like to predict something that is useful, uh, while also introducing some software to push their sponsored products, right? So that's the typical marketing and advertisement strategy. But anyway, so here again, it is like a link prediction problem, where you know what is the type of products that one would purchase for that particular class of users. Now, given that, okay, there is a similar purchase behavior, how can we predict, right? So there is an underlying graph that one could leverage and then solve prediction problem. So very similar to collaborative filtering, but also you can use this to align databases. For example, like in the picture that you see here, these are two movie databases. One is a bit more extensive, the IMDb, and the other one is like a free maintained database. And it's often that in two databases, there could be a mirror of two databases, which are basically talking about the same set of entities. But it could be that the entities, the way they are stored, are not very similar, right? So, for example, in this particular case, you see Aditya Raj and Aditya Raj Kapoor, although these are same entities, but they appear as different names. And of course, it's not as simple as a string matching problem, but you would like to look at if there is an alias in database B when you query against database A, right? So this is entity alignment problem, which is very common in knowledge graphs or to merge basically databases, right? So there are many applications of graph neural networks. Some of them have listed here, and some of them are already mentioned during the beginning of this lecture with financial applications, right? Portfolio recommend Many companies, for example, like MasterCard, NPCI in India, responsible for UPI, they use graph neural networks and other tools to enable all these AI models. Many banks also use them for fraud detection. Next to, of course, something based on handcrafted models that they have. So it's a very important tool in to have as a data scientist to know what this graph neural network is. Okay, so again, as MLP, one could spend like a few weeks understanding what graph neural networks is. But what I'll try to do is I'll try to give a bird's eye view of what is graph neural network in contrast with MLPs, and what are the problems that one could solve, right? So what does a classification or a regression mean in this particular case? To set up that context, we will introduce what a graph is more formally. So graph is basically a collection of nodes or vertices and an edge list which tells which nodes are connected. So basically, the illustration that you see here you have an edge between node 1 and 2, and this could be, say, a non-zero entry or simply a Boolean entry, right? So there's no node between no edge between 1 and 4. Then this would be a 0. This could be a 0, 1 matrix that you populate as a so-called adjacency matrix. But what is actually given to you is an edge list, which basically contains all possible list of all edges that exist in a graph between two nodes. So when you have all possible edges, then it's called as a complete graph, and often the graphs that we are interested or consider only have a limited sparse number of edges. In addition to this, what we also typically get is not just the graph, but you would also get a feature vector, a d-dimensional feature vector associated to each node. Okay. Now this matrix that we have is a feature matrix with which is of size n times d, where n is the number of nodes, d is the size of the features, number of features per node. We have all this information with us, and now the goal is to take this information about the graph, which is stored either as a matrix, which typically is the case, or you would get an edge list to begin with from which you can deduce the matrix and this data matrix X. Use that to make inferences. Okay. Now, graph analytics or graph theory is a very old area of research, right? So I'm sure, like many of you with computer science background, graph is not new to you. for example, looking at the shortest path algorithm or max cut type problems, node coloring problems. So these are typical computer science problems, but the difference is that we are now looking at both graph as well as the data matrix X associated with it together. So each vector here is basically indexed by the node of a graph. So here you have x1, which is a vector, x3 is a vector. This is indexed by the node of a graph. And what does this vector contain? This contains meta information about, for instance, the node 1. For example, in case of the Netflix prediction problem or the recommendation problem, one could include information about, say, movies, which could be the genre information, it could be directors or any attribute that is associated with that movie. And another node could be related to the user. So it could be based on the geographic location, gender, age group, etc. Right? So that is what is sitting as the attribute, which is the feature matrix. Okay. Now, as I was already telling, the edge list is a list which basically describes if there is a connection between two nodes. Now, oftentimes, to describe the operations, we need to store this edge list as a matrix or a tensor. And out of many ways, a common way to represent an edge list is through this adjacency matrix or a Laplacian matrix. So now an adjacency matrix is basically a matrix which is of size n times n, which is the number of nodes times number of nodes. And this has a non-zero entry of 1 whenever there is an edge between two nodes. So 1 and 2, there is an edge, non-zero entry of 1, right? So 1 and 3, there is an edge, non-zero entry of 1, and there's no other nodes that go from 1 other than to 2 and 3. So there are all zeros. Okay, so you start populating this matrix based on the information that is there in the edge list. Graphs can be undirected, like what that means is there's no distinction between edge from node 1 to 2 or 2 to 1. Okay, so that is what an undirected graph would mean. A directed graph would mean that there is an edge between 6 and 3, but there is no edge between 3 and 6, right? So that is what that would mean as a directed graph. So there is directionality to that edge. It can have self loops, which means that there is an edge between node 6 and 6, right? So in a graph with no self loops, the diagonal entries are all zeros, but graphs can come in different forms. It can be having directed edges. It can be with self loops and so on. Okay, so adjacency matrix basically encodes the graph structure as a matrix. Okay, that is something that is easy to remember. So now let's take a quick poll to understand the notation and sink in the notation that I introduced so far. So far, we will assume that the size of the vector for each node is the same for this ease of exposition. But in principle, the newer architectures, they can handle these feature matrices which have different dimensions of vectors for each of these nodes. Okay. Also, what I did not mention is that each edge also can have a vector associated with it, right? Which is not we are considering for now. Just for, as I said, like, okay, this is like GNN 101 lecture to basically introduce the concept of GNN. But more advanced, like if you're spending like 2 or 3 weeks, then we can handle all these different cases. But the basic idea is that you have a vector associated to a node, and potentially you can have a vector associated to an edge as well, but we'll not consider that for today. So I hope the notion of adjacency matrix is clear. Adjacency matrix has nothing to do with the feature vectors. It is basically describing how the graph is connected. Now, it is two different matrices that we work with, A and X. I can have always a feature vector. Excuse me. So I can always have a feature vector, irrespective of whether there is an edge between a node or not. Feature vector is an attribute of a node. Adjacency matrix is an attribute of connection between two nodes. Okay. The other variant that captures the same information as adjacency matrix is the so-called graph Laplacian matrix. As you can see, it is slightly it's a derived matrix started from the adjacency matrix, except for the fact that the adjacency matrix does not explicitly account for the number of neighbors of each node, which is also called as a degree. For example, in this particular case, node 0 has two neighbors, 1 and 2, right? So now if I stack that in a diagonal matrix, I get this D matrix, which is also called as a degree matrix. So the degree is basically the number of neighbors, and node 0 has two neighbors, node 1 has two neighbors, and so on, except for node 4, which has one neighbor. So that is the degree matrix. Degree minus adjacency is going to give you the Laplacian matrix. So these are two commonly used matrices. One is the Laplacian matrix. The other one is the adjacency matrix to encode the information in the graph. Okay. So now Laplacian matrix, what you can do is you can compute the eigen decomposition of this Laplacian matrix and do a lot with these eigenvectors. For example, I'll not go into the details, but if you look at, for example, one of the eigenvectors, which is the eigenvector corresponding to the second eigenvalue, that is U2, you can use that for spectral clustering. Okay, so this is a way of unsupervised learning to basically partition the graph into two partitions, right? So suppose you have a graph with two classes. Some of the nodes belong to class 0 and some of the nodes belong to class 1. Without looking at the X matrix, but if I would like to partition the graph, for example, there could exist two communities in a graph. I would like to detect two communities that are there in the graph without knowing which community that each node belongs to. I solve an unsupervised learning problem. What you would do in case of usual data is something called k-means clustering. But now, if there is a graph underlying that, you could use the second eigenvector to do spectral clustering. So this is just as a side note for information that one could use with this Laplacian matrix. So Laplacian matrix and its eigenvectors convey a lot of information about the graph itself. Okay, so now what we are interested in actually is something known as graph representation learning. So far, whenever we are looking at features of an image, we are trying to do a representation learning. And what that basically means is that imagine that I have I'm doing a classification task of two images, two class of images. One is image of dogs and image of cats. And the goal is to now build a classifier that is going to discriminate between class of images which are dogs and class of images which are cats. Now, what that means is every image that we process pass through a CNN. And if you look at the output before the softmax layer, what it is basically doing is it is going to put that image of a cat into an embedding space. And if you want to have a reasonably well-working classifier, what you require is that the images of, or the representations of images of cats are put together and images of dogs are put together so that you can simply build a classifier to separate between the class of images of cats and dogs. So that idea is called as representation learning. Now, what we are interested in graphs is also the graph representation learning, where we would like to embed each node that you see here into an embedding space. For example, as we have seen, we have a graph which is represented as an adjacency matrix, and there is also a feature vector associated with it, right? A feature as a feature matrix. Now, what we would like to do is we would like to take this information into account and pass that through some black box, which is the graph representation learning tool. It could be based on graph neural networks, or it could be based on something else. But the goal is each node that we see, I should take the graph topology structure into account, as well as the feature vector of those nodes, xu and xv in this particular case, and embed them as points in the embedding space. So this could be, for example, a d-dimensional space where x is, say, in capital D-dimensional space, right? So you would like to embed that. Now, whatever task we need to perform, right? So I can work with these embedding space because this embedding space incorporates the graph structure, which means that which nodes are connected, etc. I incorporate that and then obtain this embedding space. So this ZUs have information about the graph. It has information about X. And now I can do any downstream task with this. For example, you see that here you're looking at a node classification problem where there are three classes of nodes, class 1, class 2, and class 3. Now, if you pass this data through a graph representation learning tool, you would expect embeddings such that all the green nodes are put together, blue are put together, and red are put together. And eventually you can do a classifier, run a classifier to separate out these classes, right? So that could be, for example, done through an MLP, okay, to obtain this multi-class classification problem. So this process of obtaining these representations starting from graph data is called as graph representation learning. And what we would be interested in is a particular variant of a graph representation learning tool called as graph neural networks, okay? Where imagine that you have a black box that does some linear transformation, apply non-linearity in a particular linear transformation in a particular way. And then eventually you get representations from which we can do analytics. Okay, so we are interested in these deep learning models. But as I was telling in the beginning, graph representation learning as such is very old. There are tools not necessarily based on graph neural networks or deep learning, but there are traditional tools which can also be used to solve this same problem. Now, in this slide, you will see the three main problems that one can solve with graph neural networks or graph representation learning. In general, machine learning with graphs. Okay, so the three main tasks with graphs are the following. And any other application that you see can be casted as one of these three problems. For example, the drug interaction example can be casted as a link prediction problem, right? So this classification to basically segregate, for example, again in a drug interaction network, you would like to classify different drugs as antibiotics, analgesics, etc. So these are different classes, for instance, antivirals, etc. So there are multiple classes. You would like to classify each of these drugs into different classes. And that is node classification, right? So any of these problems can be classified into one of these three particular problems. So the first common, the main problem or with machine learning with graphs is link prediction. All these are kind of semi-supervised learning problems. So what is going on here? I have a network. Network is a graph where I have certain users, and each user has some metadata. So this could be, for example, the Facebook network or a LinkedIn network. There are already some known connections between these nodes. Now, based on these connections, what we could do is we could, for example, learn representations of these nodes through some graph representation learning tool. Now, once we have learned this representation, what you would like to do is you would like to predict if there is a link between two nodes. So then what you would do is you would pass the encoding that we have about nodes U and V through some link predicting function f to tell whether there should be a 1 or a 0, right? Or some softmax score of that, or a sigmoid score of that, to predict if there is a link between two nodes. So this could be two users in a social network. This could be, for example, an item and a user, right? Or a drug and a drug in case of a drug interaction prediction problem. Node classification, for example, in this IMDb movie database, it could be different movies, and then you would like to classify that network based on genres, right? You would like to color these nodes that are there in the movies, nodes which appear as movies into different genres. So, for example, it could be, for example, action, romance, comedy, drama, and so on. So you would like to color each of these movies based on their respective classes. It's a multi-class classification problem. Again, the goal is that you have you learn representations of different nodes. It is a node level task, and then what you would like to do is learn a classifier based on the labels that are already out there for few nodes, and use that information to predict what is a label of this. So again, you would pass that through some other uh, label predicting function, which is going to predict the label for node, right? So class label for node u. Again, how you would do that, you would basically learn these representations ZU. We have not yet seen how to learn these representations, but these are typical ways to learn the representations. Now, this is a second problem, and the third problem that is often encountered in graphs is the graph classification task. Unlike node classification or link prediction, where there is a single graph, graph classification is a collection of graphs, right? Where each graph has a label for itself. So you have like graph 1, graph 2, graph 3. There is a label associated with it. And now you would like to learn representations for each of these graphs. For example, what you would do is for each of this graph, there is like, say, nodes A to U. So you would take all you would take all these embeddings that you learn for each of these nodes. So and pass that through some function, which is basically a label predictor for that particular graph I, right? So you would basically concatenate. So this is my notation for concatenation. So you would basically concatenate for all the nodes, the features of all the nodes in that particular graph for G1, and then pass that through some function to guess a label for that particular graph, right? So the whole point in all these applications is that you have to learn representations of each of these nodes. And then once you learn representations, how you learn these representations, what are the underlying parameters to arrive at ZU, what goes in the black box, etc. We'll see. But once you have these representations, the decoding function FGH can be designed based on the task at hand, right? So that is what I described so far. Yeah. So again, once we define these tasks, the accuracy again is defined based on certain hit rates or F1 scores or accuracy precision, the usual measures. And you measure usually on the, although you call it as a test data, this is a test data for which the ground truth is known, and you use that ground truth test data for quantifying and measuring the accuracy of the model that you have built. Okay, so for example, okay, this could be the test node for the link prediction, but then in reality, you already know that ground truth, right? But you have not used the information that the link was there or not there while training the model. So now you can basically use that information to predict, to basically measure the quality of the link predictor. This is how many recommendation system works, including prediction of friends on Facebook. And of course, there's a lot of engineering that goes on top of this, but at the backbone, this is what is used in many of these link predictors. Graph classification, these are again used for mostly for bio applications, healthcare applications, where many of these molecules are compounds, right? So if you recollect your school days from chemistry, you know that okay, there is all the pictures that you see is basically a bond of a particular chemical compound, and now you would like to classify them as simple as acids, bases, and so on, right? So that is where this is used, but also for predicting newer graphs, right? So generation of new molecules is a very interesting area of research. By the way, I think I mentioned this in the beginning. One of the Nobel Prizes that was awarded this year was for this protein fold, which is an interdisciplinary endeavor between biochemistry, science, and AI, right? So, and graph neural networks plays an important role in that too, right? So that was developed. So again, here it could be like you're having molecules. You would like to classify them as different based on how acidic they are, how is it a base, neutral, right? So these are class labels. But as I told, this could also be like, for example, molecules that represent certain drugs, and you would like to classify them as analgesics or antipyretics and so on. So, right, these are typical applications of graph classification. Yeah, so indeed, that can be used to find if two representations that come as subgraphs of a knowledge graph, they have the same representation. And one simple way of looking at that as a graph classification is to have a summary token for that knowledge representation as a positive or a negative sentiment being conveyed in that database. But as I was also telling in the beginning, a very important application is this alignment, finding correspondences between two knowledge bases, right? So knowledge bases can appear from multiple databases, but then if you want to find aliases, right? So if there is like a alias entry of this particular node in the source graph, right? So when you're querying a target graph, so that is again link prediction, but across multiple knowledge graphs. So again, for software debugging, graph is predominantly used. The structure that is, you might be aware, it's called as RDF, and RDFs are also a way of storing graphs and next to knowledge graphs. So these are also often used for analytics, and graph neural networks also play an important role there. So now, having set up the context, we will see what is graph neural network. I'll look into one particular architecture of graph neural networks, and I'll tell what are the variants that are out there for different graph neural networks, and give a contrast between what we already have seen in CNNs, right? So, and why can't we simply apply CNNs is also what I will show. So recall when we were discussing CNNs, the basic idea was that I have to have a model that scales well, does not depend on the size of the input image, for which we did parameter sharing. What was parameter sharing? How was it realized? So we simply had a filter. We did a scan of that filter in that area. Okay. So we did a raster scan. And what was each filter doing? It is basically doing a pointwise multiplication and addition. Okay. And how is it multiplying? It is multiplying with the filter weights. Now, if you look at what is going on and treat that image uh, as a data or a feature that is residing on a graph, in particular a 2D lattice, what CNN is basically doing is the following. It is replacing all these pixels. How is it computing the weights? It is combining information from its neighboring pixels. What is neighboring pixel? It is all this is as defined in this graph. Okay, now if you look at the adjacency matrix, I am combining information about all these pixels, replacing that with the weighted sum at that pixel. Now, I can generalize this concept, and that is what leads to graph neural networks, where the underlying graph is not always a 2D Cartesian grid. Okay, you can have more generic graphs. But one of the problems that immediately arises that to realize that notion is, although I can replace the information that was there in all these pixels with one pixel as a weighted sum in the feature map, to go to the next slice, we did something called a sliding. That concept of sliding does not exist, or notion of sliding cannot be applied for graphs because of the irregular structure, right? So here I can have a canonical ordering to go from one direction to the other to revisit the entire image, visit the entire image. But here there is no notion of sliding. There's no notion of spatial distance. Images, I can indeed use a regular scale to measure how big an image is, right? So in terms of centimeters, if not in pixels, I can always do that. But in graphs, there is no notion of a distance, a Euclidean distance, which basically kills or defeats the purpose of doing the sliding. Okay. So now, how do we generalize this concept of what we did for CNNs to do what is similar, and that is called as convolutions over graphs. So the basic idea is the following. So whenever we have a network and there is an edge between two nodes in a network, the basic assumption is the following. If there is an edge between two nodes in the network, that basically means that these two nodes are somehow related or they share common information. Now, a way to generate representation is basically to replace the feature vector or the attribute. Suppose I have a scalar attribute, say x1, to generate a new representation that takes both graph information, the topology information, as well as the attribute information, is to simply replace that value with the average information in the neighborhood as seen here, right? So I replace x1 with x1 plus x2 plus x3 with some appropriate normalization, and I call that as y1. Okay, so that is basically analogous to what we did in CNNs for images, where I'm replacing the information in that neighborhood by some average, a weighted average, with weights that are learned based on the task. Okay, so that notion extends to graphs and is called as graph convolutions, where you replace the information at that particular node with the aggregate information of the features present at that node, present at the neighborhood of that node, where Ni indicates the one hop neighbor of that node I. Okay, so for all nodes that are in the one hop neighborhood of node I, I'm replacing it with that value. You do this for all the nodes. Now, what does it do? when you're computing this average, note that you're not simply averaging the features at all the nodes. I'm not replacing x1 with y1. That is summation over all the nodes, but it is summation over only those nodes in the neighborhoods. That is how you are incorporating the graph information. This information can be compactly represented as this operation A times X. X is our feature matrix. A is the adjacency matrix. So I'm replacing the features with the average information that is there in its neighborhood. For example, X1 for this particular graph, which does not have any neighbors, one node does not have any neighbors, you have X1. This is not for this graph, but some illustration. If particular node 2 has this neighborhood information, you are replacing that with its average and so on. So that operation that I just described for all the nodes can be replaced with this. Now, instead of using an unweighted sum, I can always introduce some weights which are going to figure out what these weights are, how to appropriately combine information from my neighbors. How should I weigh information from node 2 and node 3 while computing the features of node 1. Okay, so this operation, now instead of doing it for all the pixels, I'm simply doing it for pixels near me, and near is characterized by the neighborhood. Okay, so near and far was kind of canonical and conventional when we look at any uniform graphs or uniform grids which are natural to images. When there is no regular ordering, the notion of nearness is defined by the neighborhood information. So I'm replacing all the information that is out there with the information from my neighbors. Okay. So again, this is another illustration. Now, if I repeat this operation again, say I have I have AX, I get one hop information. Now I do A square X. So what you're basically doing is you're doing A times AX. Now A times X, what did that do? It is basically combining information from its neighborhood to arrive at new features. Now if I do again A times Y, the information at node 1, X1 was replaced with Y1, okay, and a Y6 and so on. Now if I do A times Y, it is now again replacing information with y1 with some other z1, which takes into account all this. But this ay can be viewed as a times ax. But if you look at what a square is doing, it is aggregating information from two hop neighborhood, not just one hop neighborhood. So now, depending on how deep you want to go to aggregate information, whether I want to use my one hop neighborhood or two hop neighborhood, two hop neighborhood of node 1, for instance, is node 6 and 5 and 7, right? So these are two hops away and 4 as well, right? So not just one hop away, but two hops away. So depending upon how much deep we want to go while extracting this information, we can go with ay, a square y, a cube y, and so on, okay? So these are basic operations to gather information from different hops. Now, these things are put together to define what is known as a graph convolution. Let's take this poll to reflect what we just discussed so far. Let me end this poll in a few seconds. So we are now defining convolutions over graphs, and you already get a story. So convolutions, basically what we are doing, point-wise multiplication and addition in case of images or one-dimensional signals. When we have graphs, the graph convolution is again doing something similar. It is doing multiplication and addition, but the addition is not over the entire um, nodes, but it is defined over the neighborhood, which nodes are adjacent to those nodes. So AX combines information from one hop, A square X combines information from two hop, and so on. So do you have any questions so far at this point? Is the basic idea behind forward extension of what we did? All we need to do is to introduce a learnable matrix. Okay, so if you look at this, what we're basically doing is I've combined information from the first hop neighborhood, but then I transformed that. So before, all we did was we did X times W to get a linear transformation, apply nonlinearity subsequently. But now, instead of simply doing A times X times W, I do A times X and X times W. Now, if you look at the size of W, suppose A is N times N, X is N times D, A times X is N times D, and W is some D times small d. So what we have basically done is we have made this W matrix independent of the number of nodes. Irrespective of how big the graph is, you can have a billion nodes, but my W need not be of size of billion, right? So first I incorporate the graph information through this A times X operation, and then do a transformation using this W matrix, okay? So now in a graph neural network, typically what is done is you do this at multiple layers. You do a GCN layer, which is a graph convolution layer, multiple times to go deeper into network. So you just do one hop aggregation, linear transformation. You do that multiple times, and every layer you do this particular operation with nonlinearity. Okay. So that is a graph neural network. You can have a bias as well. The only difference is that we are replacing the usual convolution operation with a graph convolution operation that takes the graph structure into account. Okay, so that's basically a single layer of graph neural network where you're aggregating information from its neighborhoods, right? So again, I think this is a poll question that I'm going to skip, where a single layer graph neural network is basically aggregating information from its one hop neighbors and then doing a transformation through a learnable weight matrix and biases. So when we think about deep graph neural networks, what we are basically doing is we are doing a cascade composition of several such nonlinear functions where you should focus on this particular equation where first I do AX with W1, apply some nonlinear activation function sigma, and then the new features, you're again doing A times this new set of features that you get, again doing a linear transformation. So every time we are working with one hop aggregation, which is very similar to what we did with CNNs, right? So how did I get information from the faraway pixels? So every time, if you look at this image, although in the at this layer, I'm only combining information from this pixel, these pixels, and this I'm combining from this. Now, when I have the second layer of GCN, the second layer of convolution neural networks, what it basically does is it does a convolution filter on this layer, which is aggregating information from all these pixels, but the first layer is only getting information from its neighbors. You take to the first feature map. The first feature map, when you look at what are the pixels that are neighboring in the feature map, these are informations from different patches. Okay, so that is what is also going on in graph neural networks. As you see here, in the first layer, you are getting information from one hop, and the second layer, that is what we do here, you're getting information from the two hops. So you're getting going more deeper and deeper with more number of layers. So you have input features, you get information from the first hop neighborhood. You have one more layer of GCN, you gather information from the second hop, right? So this is how you gather information about what is going on in the graph structure, as well as combining the attributes. So once you do all this, you're basically extracting the features that are relevant for this particular task. How do you learn these W1s, W2s, and so on? Very similar to what we did before with backpropagation. So once you have that, you can use that for a particular task at hand to do a forward pass. But to train this W1, W2, the weights and biases, so I have not shown biases here, but you can have potentially biases, and weights and biases are learned by the task at hand, basically using the labels that you have. So what you basically see is an illustration of what is going on in the graph neural network in a slightly elaborate way. So it is also called as message passing, where we have initial features at the kth layer. You aggregate that information. By aggregate could be a plus, a summation information, or some other complicated function. The abstract way of writing this is the aggregate function. Once you have that, you update the feature of the node U by this aggregated information, by combining with whatever information that we have with that's the self information and the information from the neighborhood. Okay, so now choosing different aggregation functions, different W's and W self, W neighborhood, there are different architectures that are out there. Okay, so that's graph neural networks in the most abstract way. And the way W's are learned here are based on the task at hand. Okay, so now let's take a look at this poll to understand what to basically reflect back on what we understood about GNNs. So how do I get information from multiple neighborhoods? And easy way for you to appreciate what is going on is to contrast between the CNNs, where, as I said, like each layer of a CNN, you are gathering information from one particular patch. But the way you are combining that information is at the next layer, where again you implement a filter where you are gathering information from the neighboring pixels in the first feature map. But if you look at what is that information sitting, this is the information sitting in the adjacent patches. Let's end this poll now. So more deeper we go in the graph neural networks, you are aggregating more information, right? So now just to again restate, so what we have is an n by n adjacency matrix, an n by d feature matrix. N is the number of nodes. What we are expecting at the first layer with an appropriate learnable W is a feature. That is Y, which is n times P, which means that if you look at nodes U and V, the vector of the feature should be a p-dimensional feature vector. Now, whatever downstream task we have, we work with these features. Okay, let's to quickly summarize what we have done so far. Maybe I used capital D instead of small d, and small d instead of p, but the message is the same. Now, what we will do is in the reminder, 5 minutes to 10 minutes, we will look at different applications and see how one could basically use these features that we learned to enable these tasks. So a common pedagogical example similar to this MNIST database in the graph learning parlance is this Cora data set, which is the database of academic publications. Okay, so the basic goal is the following. So there are about 3,000 publications which are corresponding to nodes in the graph. So there are about 3,000 nodes, and edges are basically capturing the interaction between two publications as if one publication refers to the other. Okay, so in this particular network, there are about 5,000 odd edges. But if you look at any large scale Twitter type networks, there are easily about a million nodes and a billion edges, right? So that's typically the scale of the problem. Now, the goal is similar to this movie example. The goal is to capture and classify what are the subjects underlying the publication. For example, this could be from physics, chemistry, math, biology, and so on, right? There are 7 subjects from which the papers are taken. So now there's a graph. Each node has a one hot encoding about the what the paper is about, right? So it could be a summary of that paper, or it could be the summary of keywords of that paper. That is the attribute. So there is some metadata sitting on each of these nodes. Now the goal is to train this network to classify, partition, say papers from computer science and papers from physics, right? So in case this is a 2-class classification, you would get something like this coloring. But in this particular case, we have a 7-class classification, a multi-class classification. So now what you would do is you would take this information, pass that through a graph neural network, several layers of graph neural network, and then eventually at the output layer, you should have a multi-layer perceptron as always. So this multi-layer perceptron in particular, the last layer, you would have a softmax layer, which is basically measuring the discrepancy between the label for that node U and which is basically the subject from which it belongs and the embedding, right? So it's going to minimize the discrepancy between these two. And this loss function will, of course, depend on all the weights and biases of the graph neural networks and if there is an MLP and so on. But at the last layer, you have a soft. So a simple way to implement that in the stellar graph TensorFlow is basically very similar to what we have. Instead of a dense layer, you would simply have a GCN layer, right? So that's going to give you the embeddings, and either you can directly work with the embeddings of the GCN layer, or you could use an MLP, one more MLP at the end, okay? So this is for node classification, right? A multi-class node classification. As you see, the philosophy remains the same. The only thing that is changing now is that we have the embeddings that are coming from a GCN layer. Now, for a graph classification, what you basically have is for each graph, you would get these embeddings Z1 to Z2. Only thing that we will do is we will combine the embeddings of all the nodes to get an aggregate embedding of the entire graph. So I have Z1 to Z, say 100. I have embeddings of all the nodes. Now in graph classification, I would like to get one embedding for the graph, and that is achieved through this mean pooling. And once you have this mean pooling, I can still again like do a classification to basically classify different graphs based on the labels that I have. And again, you would set up a loss function to minimize the discrepancy between the label and the embedding of that particular graph. So once you have basically the graph neural network that generates the embeddings, you can use that for different one of the three tasks as we discussed. So just to again reflect back, let's take this last poll for the day. And I think I have one more application. To end this session. So if you're using graph classification, now the question is how do you use the representations? So GNNs, recall that every for every node you get an embedding, right? So it's going to take the attribute information along with the underlying graph structure, put that in the embedding space. Okay, now that means that if a graph has 50 nodes, you have 50 embeddings. But now when you're doing graph classification, the label is for that particular graph, the entire graph. Okay, so now what we are trying to see is how should we go from these 50 embeddings to one embedding that I can work with. And so that's this poll about. I'll end this now. And as I was explaining, what we would do is we would combine that information through an average of all the nodes or a mean pooling operation. Okay. The final example that I have is for this link prediction, which is a prediction of this users in social network. So here, one simple thing that you could do is, suppose I have the embeddings that I learned from GCN. Now, if you want to predict if there is a link between these two nodes, a simple decoder could be to measure cosine similarity between these two, or it could be simply a logistic function of the inner product between these two. If these two features are correlated, then they should have a link between those two, right? So that's one example. Or you can have a weighted decoder with some weights. Instead of simply checking for correlation, you can also have a decoder that is learned. Okay, so these are example decoders, and you could use one of these decoders where you also learn this W. In this case, there is no learnable. So you're simply saying that, okay, if these two features at the output layer are correlated, let me pass that through a thresholding function to say whether there's a 0 or a 1, or you could do that with some learnable parameters. So here the example is like for classification by looking at video frames to one of the tasks, right? So it could be like node classification, but it can also be link prediction, where again in this publication example, you're looking at this network of publications, and then what is the likelihood of two people collaborating with each other, right? Or two people being friends of the other. So these are some applications, three main applications that are often dealt with machine learning with graphs. As I said, okay, this was like a quick 1.5 hour session to make you aware of what is going on with machine learning with graphs. If you're interested, there is like a whole bunch of topics that one could spend time with machine learning with graphs. For example, what is the graph generation, generative algorithms, or how is graph being used in LLMs? So a combination of what is kind of the traditional topic with this new topic, or how can GNNs be used for different applications that you could come across, right? So there's a lot to study, but what I try to take you through is a basic notion and give you a sense of what is going on with graph neural networks. So that basically kind of concludes the neural network models that we planned for this module. One is we started with the MLP when the data is predominantly unstructured. Next, we started looking at structured data whenever we have images where you can exploit these structures. Next, we started looking at sequences where you could do time series forecasting prediction problems, also to learn something from the past. Today, what we saw was relational data. So it is again type of a structured data, but the structure appears as a graph. And how do we learn representations? How do we solve downstream tasks with that relational data? Along these lines, we have also seen what are generative models that could potentially use one of these. For example, the GAN variational autoencoder, you can also use it with CNNs. You can also use a similar idea with graph neural networks, right? So that combination is always possible, or a combination of graph neural networks and RNNs if you have time series data over graphs. So that is again what is what people have studied. So this gives a sense, basic essence of different neural network architectures out there. Now, what we will do in the next lecture is slightly deviate from the usual architecture and introduce something known as an attention mechanism. And attention mechanism and a particular usage of attention mechanism in this transformer architecture. With the goal of studying that, I'll introduce what are the NLP use cases, or how to do some of the NLP tasks using deep learning, particularly using transformers, and look at one of the initial versions of the GPT models, right? The BERT transformer. So that is what is pending in this particular module, and that will be the topic for the last day. In addition, what we will also do is we will reserve some maybe an hour or so for revision, where I will take you through the entire set of contents that we have for this module. What we also typically do is we will send out a questionnaire where the basic idea is that what I'll do is I'll take you through that NLP module for 1.5 hours or so, maybe 2 hours. And then the remaining hour, it is kind of an open forum where I'll let you also interact, all of you, and I'll of course moderate. But to make sure that the revision part is effective, what I will do is I'll ask the talent sprint team to also send out a circular, a survey where you are identifying what are the topics that you would like me to concentrate or revisit, etc. Right? So I would basically organize that lecture according to that survey as well. Yeah, so that brings me to the end of today's lecture. So I'll be happy to take any questions that you have at this point, or we can happily break for lunch and resume back next week.
Professor, I have a couple of questions, not related to today's, but to some of the previous lectures. When we use early stopping, we typically minimize, we monitor validation loss in the mode of minimization. But there are other parameters also where we can actually monitor accuracy like metrics, and in the max mode, maximizing accuracy. Is that max mode generally useful in any situation? Because when it comes to early stopping specifically.
Yeah. So see, the basic idea behind early stopping is if you have a model that is not deteriorating with more training.
Yeah.
That is when you early stop.
Yeah.
So for example, if accuracy is a measure, like when you're doing classification, mostly it is accuracy.
Yeah.
Or 100% minus accuracy is treated as loss.
Yes.
But MSE is loss, right? So there's no notion of accuracy. But so for example, your MSE, you are looking at, say, lower the better, and 10 power minus 3, 10 power minus 5. And
Yeah.
more you train, it is shooting up.
Yeah.
Now, what that basically means is that you can use a model that was giving you the best accuracy, or the best loss that you have seen so far.
Yeah.
So that is when you would stop, and indeed that's based on the validation, right? So
Yeah.
both both based on training loss and validation loss.
Yeah.
Say I can elaborate further. Just try to create a new slide. So typically what happens is that whenever you're training a neural network, right? So the goal is that there is a loss function, and that loss function has some minimizer. So imagine that there is a valley and
Yeah.
you're dropping a ball, and then that should go down the valley.
Yes.
Now, if there is one particular valley point, wherever you drop the ball, it will converge to that particular point, right? So
Yeah.
that is this valley I'm talking about. And
Correct.
the picture that I'm trying to draw here is like from looking from the top. Okay. So now imagine if this was the case, then it doesn't matter where you stop, it is always going to settle down here.
Yeah.
And doesn't matter how many iterations you do, it's not going to go out of that.
Hmm.
Now, this is a very nice case, which is never encountered while training a neural network. Oftentimes, what you would have is you would have something like this.
Multiple.
Yes, right. So this is called as this will basically have multiple minimas. So one way to see this is like something like this.
Yes.
Depending upon where you initialize, you could potentially initialize from here, and this is going to give you, say, an accuracy of 97%, and this is accuracy of 85%.
Yeah.
Okay, now when you're training a neural network, you could, for instance, start with your initialization from this point,
Yeah.
and oops, yeah, and then you would do iterations, and then it can be at this point. Now, it can stay at this point, say for epochs 100 to 200.
Yeah.
If you continue, it could happen that it is going to escape out of this and go to this point, which is going to give you, say, an accuracy of 80%.
Yeah.
So now you see that it is increasing.
Yeah.
Now, it could be that you train further, it can find this point,
Yeah.
but that is never known, right?
Yes,
So
yes.
now from here, okay, this is at 120, and this can appear at, say, 1200 epochs,
Yeah.
right? So, but now either you keep on training with the hope that there is something better,
Yeah. Yeah.
or you could simply stop at this point, right? So that is basically what happens when you're escaping from one point to the other,
Mhm.
right? So that is because of the landscape of the problem. Now, the way you measure is not um, really deciding factor of how to early stop, but how
Mhm.
you measure depends actually on the task at hand. For example, it doesn't make sense to use, say, a loss function to quantify classification, right? So, for example, I have, say, labels in my mini batch, which is
Mhm.
like, say, 0.9. This is like with respect to mini batch size, right? So, MB times 1.
Yeah.
And then, so, say, mini batch is, say, 0.8. Now this the true labels are 1, 0, and then up to 1. Now you would not measure the MSC between these two, right? That doesn't make sense because I can still get a very low MSC, but if you look at point wise, the accuracy can be hopeless,
Yeah.
right? So what I'm trying to say is that the way you measure accuracy or loss, the choice of that depends on the task at hand. Okay, and the early stopping, you always it is better to use the loss that we pick.
Yeah. Yeah.
Okay.
There was
Now,
significant difference when while maximizing accuracy versus
yeah.
minimizing
So, I
loss.
mean, see, I mean, like you can have basically, say, for this classification, we can cook up examples where
Yeah.
the loss function is, say, close to 10 power minus 5, and the accuracy is 40%.
Yeah. Correct.
So,
Yeah.
both of them would not convey the same story.
Yeah. Yeah. Right.
Although, I mean, you can measure that loss, there is a reason why we use different loss functions.
Yes. And Professor, another question. Does batch normalization usually help for small sized batches like 32 or 64 with small sized data sets? Because it has
Batch
usually not helped.
normalization always helps. Maybe that is one topic that I did not get time to discuss that during uh,
Okay.
I think I wanted to do that between like week 1 and week 2. I did not get to do that. I'll do that in the revision week.
Yeah.
So batch normalization is always preferred to, it's preferred, and one way to easily understand batch normalization, which I will anyway elaborate when more people are around.
Yeah.
In the initial layers, what we always do is we do normalization. For example, for this MNIST data set, I showed that you have grayscale image between 0 to 255 value. You always bring it out between 0 and 1 through normalization. Simply dividing by the maximum value, you do normalization.
Yeah.
But if you recollect, the loss function, the activation function, the sigmoid activation function was something like this.
Yes.
And if you recollect the discussion from the MLP week, that we wanted the gradient to be non-zero value, something that changes for the update to be meaningful. And if you
Yes.
look at this region, the gradient is 0. So we would always like to operate in this region. Now, what batch normalization basically ensures is that at each layer, it is going to bring the data points between this window. We
Oh.
did that for the initial layers, but so once, okay, the initial data point is X. I can normalize, bring it between 0 and 1. But after I multiply with W, I can basically get, say, anything, right? So I can multiply with small W's, and that can go beyond 1.
Yeah.
Right. So for example, like I can have like a 0.2 and a 0.3 and something else, and I keep on adding that, right? That is what we do when we do W times X, and that can go to 2. And if I look at the output at this point, that might be at this range where the gradient is 0. So I need a mechanism to bring it down to this particular range, and that is what batch normalization does. So it's always good to do batch normalization.
Okay.
Hmm.
I mean,
And that helps in, so whenever you see that the network is not training, or
yeah.
you're supposed to get like an accuracy of 90%, but it is saturating at 60%,
Yeah.
or it is not changing too much from the initialization. The random initialization was already giving
Okay.
you, say, 55%, and after training for hundreds of epochs, you're only getting 57% accuracy. So then
Okay.
that basically means that either you're hitting a saturation region of your activation function, which is not allowing the weights to change significantly compared to what you initialized with. So in
Okay.
that case, we have to do batch normalization. It's worth a bit more discussion that I will include in the revision week.
Okay. I mean, just does it help when the training data, the samples are very different from each other? Does it help in such a case? Because I mean, I had seen that it did not help much in some of the many projects.
It
Or
will not harm, at least.
okay.
That is how I would put that, right? So uh, it it might not help in increasing the accuracy,
Okay.
but it might help in achieving the same accuracy with fewer epochs.
Okay.
So it might help to do so. Most of the cases, it will not worsen, because the number of parameters that we introduce with batch normalization is minimal.
Okay.
And it's again a design choice, whether to do it every layer or once in few layers.
Okay.
That's a choice that one should make.
Okay. Okay.
Yeah.
Thank you.
Okay. Okay, so we'll take the question on the chat. Sridhar, I don't know if he's still around.
Yes, I am, sir. Yes.
Yeah. So, yeah, cosine similarity, to just convey that idea is a way to do that, right? So, but you can also use something that's much more involved. But the basic idea is that, okay, if two features are similar after all this aggregation and learning, then you would like to put an edge, right? So that is the basic idea. And one way to measure is correlation. The other way to measure is through this learnable decoder. And often, most of the problems in link prediction, it is with undirected graphs. Very rare that somebody predicts links with directed graphs.
Professor,
So
in
it's like
terms of let's say root cause analysis prediction or some it would require a directed graph, right?
Yeah, so that, yeah, I mean, so there are some cases like, yeah, I mean, so if you want to do some kind of a causal analysis, then you would do this, but then they would not use such a decoder, right? So it will be mostly uh, uh, a sequence predictor that you would use, right? So which is the trajectory that you would visit one after the other, right? So you would know, say, for example, I'm at node V and then I have to go to node U or node Z, right? So that is that naturally takes into account the orientation or the directedness of the edges.
So possibly adding temporal features.
Temporal features, but one way, imagine the, let me try to draw. So for example, like, I mean, now you're doing route, say, analysis or trajectory prediction, and you are at, say, you have visited node 1, 2, okay, through that analysis, and now you're looking at whether uh, say 2 was causing 3, or which one to go next. Okay, so either you go like this or this. Now what you would do is basically you would fix the orientation in that case. So whenever you're doing such analysis, the sequence is kind of fixing the orientation, and that is not necessarily derived from the edge information itself. I hope that.
Got it. Yeah.
So
So,
because of the causality, that is already kind of taken care.
got it. So in essence, basically, link prediction, as you discussed, would result in undirected edges, but
Yeah,
we'll have,
correct.
yeah, okay.
Yeah. So in recommendation systems, we also have a frequency pattern, which is, so Brindaban, it's a mix of both, right? So if you ask what is Netflix using, it will use uh, all possible tools that are at their disposal, right? Graph neural networks and other results that are consequence of mining. There's no, it's an engineered solution, but that is to suit that particular domain. You could simply, I mean, and then frequency pattern or other mining requires some domain expertise. Whenever you have that domain expertise, it's better to augment that. But otherwise, just like any other deep learning tool, this is doing that feature extraction without the need for such a domain knowledge, right? So that is what I would say.
Okay. So I was actually following for that market basket analysis kind of recommendation system.
Yeah. So yeah, I mean, so if there is some additional information, either you could put them as node features uh, and include them, or you could basically use the GNNs as a pre-screening tool that is going to generate a set of recommendations, and then a domain expert is further going to look into that and then look into that pre-screened list. Instead of like looking at 1,000 commodities, now he's going to look at, say, top 10 commodities, and then do
Okay.
some further social and engineering uh, additions to that.
Okay. Got it. Thank you.
Okay. Okay. So if there are no further questions, then let's conclude today's lecture. I hope that was useful, and I'll see you in the next class. Thank you all.
Professor,
Yes.
yeah.
Is the next lectures contents, as part of the exam?
No. No.
Okay.
Yeah, so NLP, it was so we did not include that and in the exam. So it was like basically in the last cohort onwards, because of the popularity of all this LLM, it was kind of an addendum to uh, the module. So typically, yeah, so that's why it's a mix of both revision and this NLP, right? So that is what we have, and it's not part of the exam.
Thank you.
Yeah. So yeah, again, like so the exam is kind of like it's not like one, right? So one time window, it's released, but then whatever is covered till today, that is what you will see in the exam, right? So it will be made available, and then you have like I think I don't know. Don't hold me for this. Like maybe there's a couple of weeks. Raju can correct me. So you have a few weeks to complete the exam. Few may not be few, at least like week or two. Okay, so thank you all. Let's conclude this meeting now.
Thank you, Professor.
Thank you.
Thank you, Professor.